So the largest objects in the universe are so absurdly massive that they genuinely shouldn't exist. Like, I'm not being dramatic here, I mean that quite literally. There are structures out there in the cosmos that are so large, so incomprehensibly vast, that according to every model we have, according to the fundamental principles upon which modern cosmology is built, they simply should not be there. And yet they are. We've mapped them, we've studied them, we've measured them, and we have no idea how to explain them. We're talking about walls of galaxies stretching across 10 billion light-years of space. Black holes so massive they contain the equivalent of 66 billion suns compressed into a region smaller than our solar system. Galaxies with 100 trillion stars, 50 times wider than the Milky Way, that formed through billions of years of cosmic cannibalism. Structures so large that light takes 4 billion years just to cross from one end to the other. And here's the kicker. Some of these objects are so extreme that their very existence challenges the cosmological principle, the foundational assumption that the universe is supposed to look the same in all directions on large enough scales. If that principle is wrong, and these massive structures suggest it might be, then we need to seriously rethink everything we thought we understood about the universe. Now, I've researched this topic more times than I can count, and every single time I sit down to actually comprehend the scale of what we're talking about here, my brain just kind of shuts down. The numbers are so large, they've completely lost all meaning. But we're going to try anyway, because if there's one thing I love doing, it's hurting my own brain trying to wrap my head around cosmic scales that make absolutely no sense. So let's start small and work our way up, because in order to understand just how massive the largest objects in the universe really are, we first need to understand where we actually are in all of this. So, we're going to talk about the largest objects in the universe, which, to be honest, is a topic that never fails to absolutely blow my mind. Like, I've researched this topic countless times, and every single time I sit down to actually comprehend the scale of what we're talking about here, I'm left just staring at my screen thinking, how is any of this even real? The universe is incomprehensibly massive, and the objects within it are so absurdly large that our brains genuinely struggle to even process the numbers involved. But we're going to try anyway, because if there's one thing I love doing, it's hurting my own brain, trying to wrap my head around cosmic scales that make absolutely no sense. Now, before we dive into the truly massive structures that exist out there in the cosmos, structures so large they shouldn't even exist according to our current understanding of physics, we need to establish where we actually are in all of this. Like, what's our cosmic address? Where do we sit in this incomprehensibly vast universe? Because to understand just how big the biggest objects in the universe are, we first need to understand the ladder we're climbing to get there. And trust me, it's a long ladder. So let's start small. Well, relatively small. Let's start with Earth, because that's where we all are right now, presumably. Earth has a diameter of about 7,918 miles, or if you're using the metric system like a normal person, 12,742 kilometers. Now, to us, that's massive. Like, you could spend your entire life traveling and still not see every corner of this planet. But in cosmic terms, Earth is absolutely tiny. It's a speck. It's less than a speck, actually. It's like a grain of sand on a beach that stretches on forever. Earth orbits the Sun at a distance of about 93 million miles, which is what astronomers call 1 astronomical unit, or AU for short. The Sun itself is absolutely massive compared to Earth. We're talking a diameter of about 865,000 miles, or 1.4 million kilometers. That's about 10 times the size of Jupiter, which is already the largest planet in our solar system by a significant margin. Like, you could fit over 1,000 Earths inside Jupiter, and you could fit over 1,000,000 Earths inside the Sun. The scale is already getting ridiculous, and we've barely left our own neighborhood. Our solar system extends out to what's called the Kuiper Belt, which sits at around 50 AU from the Sun. That's 50 times the distance between Earth and the Sun. This is where you'll find Pluto, which, by the way, is still a planet in my heart, regardless of what the International Astronomical Union says. The Kuiper Belt is essentially the edge of our solar system, at least in terms of where the majority of objects influenced by the Sun's gravity hang out. Beyond that, you've got the Oort cloud, which is even more ridiculously far out. But we're not going to get into that right now because we've got much bigger fish to fry. So we've established our solar system. Now let's zoom out, way out. Because our solar system is just one tiny system orbiting within a much, much larger structure, the Milky Way galaxy. And when I say much larger, I mean incomprehensibly larger. The Milky Way has a diameter of somewhere between 100,000 and 180,000 light-years. Now, if you're not familiar with what a light-year is, let me explain, because this is a crucial unit of measurement we're going to be using a lot in this video. A light-year is the distance that light travels in 1 year. Light moves at about 186,000 miles per second, which is the fastest speed possible in the universe as far as we know. Nothing can move faster than light. So in 1 year, light travels approximately 5.88 trillion miles, or 9.46 trillion kilometers. That is 1 light year. Just to put that into perspective, the closest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means if you were traveling at the speed of light, which again is impossible for anything with mass, it would still take you over 4 years to get there. And Proxima Centauri is our closest stellar neighbor. It's right next door in cosmic terms. The Milky Way, as I said, is 100,000 to 180,000 light-years across. Earth sits about 26,000 light-years from the center of the galaxy in a little region called the Orion Arm. The Milky Way contains somewhere between 100 billion and 400 billion stars, and that's just the stars. We're not even talking about planets, asteroids, black holes, or any of the other countless objects floating around in there. So yeah, the Milky Way is big, really, really big. But here's the thing, the Milky Way is just one galaxy. There are an estimated 200 billion to 2 trillion galaxies in the observable universe. Let that sink in for a second. 2 trillion galaxies, each one potentially containing hundreds of billions of stars. The numbers are so absurdly large at this point that they've basically lost all meaning. Like, our brains just aren't wired to comprehend numbers that big. But we're going to keep going anyway, because believe it or not, we're still just scratching the surface of the largest structures in the universe. Now, galaxies don't just float around in space all by themselves like lonely islands. They tend to hang out together in groups and clusters, bound together by gravity. And this is where things start to get really interesting. You've got what are called galaxy groups, which contain anywhere from tens to a few hundred galaxies, all gravitationally bound to each other. Our Milky Way, for example, is part of what's called the local group. The local group contains the Milky Way, the Andromeda Galaxy, which is the closest large galaxy to us, and about 50 or so smaller galaxies. It's a pretty modest group as far as galaxy groups go. Now, Andromeda is actually on a collision course with the Milky Way. In about 4.5 billion years, these two galaxies are going to smash into each other and merge into one massive galaxy, which astronomers have already nicknamed Milkomeda, because of course they have. Don't worry though. When I say smash into each other, it's not like the stars are going to be colliding. Space is so incomprehensibly vast and empty that even when two galaxies merge, the stars just pass by each other like ships in the night. The whole process will take a few billion years, and by the time it's done, the night sky from Earth, assuming Earth is still around, will look completely different. It's honestly a fascinating process, but that's a topic for another video. So, we've got galaxy groups, which are relatively small collections of galaxies, but then you've got galaxy clusters, which are much, much larger. Galaxy clusters contain hundreds to thousands of galaxies, and they span a few million light-years across. One of the most famous examples of a galaxy cluster is the Virgo cluster, which is about 54 million light-years away from us. The Virgo cluster contains somewhere between 1,500 and 2,000 galaxies, and it has a total mass of about 1.5 quadrillion times the mass of our Sun. Like, what does that even mean? A quadrillion? That's a 1 followed by 15 zeros. It's a number so large that it's genuinely difficult to conceptualize. Now, here's something really interesting about galaxy clusters that I want to touch on, because it's absolutely crucial to understanding how these massive structures even exist in the first place. You see, if you just look at the visible matter in a galaxy cluster, the stars and the gas and all the stuff we can actually see, there's not nearly enough mass there to hold the cluster together. The galaxies are moving so fast that they should just fly apart, but they don't. And the reason they don't is because of something called dark matter. Dark matter is this mysterious substance that we can't see, we can't detect directly, but we know it's there because of its gravitational effects. It makes up about 85% of all the matter in the universe. That means that for every 1 kilogram of normal matter, the stuff that makes up stars and planets and you and me, there's about 6 kilograms of dark matter. Astronomer Alex Filippenko put it really well when he said, if you only had the visible stars, the galaxies wouldn't be bound together. Dark matter is the glue that holds galaxy clusters together. Without it, these massive structures would just disintegrate. And to this day, we still don't know what dark matter actually is. We know it's there, we can measure its effects, but we have no idea what it's made of. It's one of the biggest unsolved mysteries in all of physics, and it's absolutely essential to the existence of the largest structures in the universe. So galaxy clusters are massive, but we're not done yet. Because galaxy clusters themselves are part of even larger structures called superclusters, and this is where things get truly mind-blowing. Superclusters are collections of galaxy clusters and galaxy groups, all loosely connected by gravity, spanning tens to hundreds of millions of light-years. Our local group, along with the Virgo cluster and about 100 other galaxy groups and clusters, are all part of what's called the Virgo Supercluster. The Virgo Supercluster is about 110 million light-years across, and it has a mass of about 10 to the power of 15 solar masses. That's a 1 followed by 15 zeros again, but this time we're talking about the mass of the Sun, not just any random unit. The Virgo Supercluster was discovered back in the 1950s when astronomers noticed that galaxies in our region of space weren't just moving randomly, they were all flowing toward the Virgo cluster, which sits near the center of the supercluster. This flow of galaxies is caused by the immense gravitational pull of all that mass concentrated in the Virgo cluster. Our local group is essentially in orbit around the Virgo cluster, slowly being pulled toward it over the course of billions of years. Now, for a long time, astronomers thought the Virgo supercluster was our cosmic home, like that was it. That was the largest structure we were a part of. But then in 2014, a team of astronomers led by a guy named Brent Tully published a paper that completely changed our understanding of our place in the universe. They discovered that the Virgo supercluster is actually just a small part of an even larger structure, a structure so massive that it dwarfs the Virgo supercluster in every conceivable way. They called it Laniakea, which is a Hawaiian word meaning immense heaven, and immense is an understatement. Laniakea is about 520 million light-years across. It contains roughly 100,000 galaxies. Its total mass is estimated to be around 10 to the power of 17 solar masses. That's 100 times more massive than the Virgo supercluster. Let me say that again. Laniakea is 100 times more massive than the Virgo supercluster, which itself is already incomprehensibly massive. Like, at this point, the numbers are so large that they genuinely mean nothing to our human brains. We simply do not have the capacity to comprehend scales like this, but we can try, and that's what we're doing here. Now, what makes Laniakea so special isn't just its size, it's how it was discovered. Previous definitions of superclusters were based purely on the positions of galaxies. Astronomers would look at where galaxies were in space and group them together based on proximity. But Tully and his team took a different approach. They mapped the velocities of galaxies, looking at how they were moving through space, not just where they were located. What they found was that all the galaxies in this region of the universe, including our Milky Way, are flowing toward a common point. They're all part of the same gravitational basin of attraction. It's kind of like how all the water in a river flows toward the ocean. All the galaxies in Laniakea are flowing toward a region of space called the Great Attractor, which is located in the Norma cluster. The Great Attractor is this incredibly dense region of space with an enormous gravitational pull. We're moving toward it at about 2 million miles per hour. 2 million miles per hour. And we don't even feel it. That's how vast space is. You can be hurtling through the cosmos at 2 million miles per hour, and it feels like you're sitting still. The Great Attractor is pulling in everything around it, including our galaxy, and there's nothing we can do about it. But here's the kicker. We're never actually going to reach it. And the reason for that brings us to one of the most important concepts in all of cosmology, dark energy. You see, the universe is expanding. It's been expanding ever since the Big Bang, about 13.8 billion years ago. But not only is it expanding, it's expanding faster and faster over time. This acceleration is caused by dark energy, which is yet another mysterious substance that we don't fully understand. Dark energy makes up about 68% of the total energy content of the universe, and it's driving the expansion of space itself. On small scales, like within our solar system or even within our galaxy, gravity is strong enough to overcome the expansion of space. But on larger scales, dark energy wins. And once you get beyond about 10 million light-years or so, the expansion of space starts to dominate over gravity. Alex Filippenko explained this really well when he said, "The universe is expanding faster due to dark energy." What this means is that superclusters like Laniakea aren't actually fully gravitationally bound. They're not going to stay together forever. Eventually, over the course of hundreds of billions or even trillions of years, dark energy is going to pull them apart. The galaxies within Laniakea are going to drift away from each other, and our cosmic home is going to dissipate into the expanding universe. It's kind of a depressing thought, to be honest, but that's the reality of the universe we live in. Nothing lasts forever, not even the largest structures in existence. So, to recap, because I know we've covered a lot of ground here, we started with Earth, a tiny planet orbiting an average star in the suburbs of a fairly typical galaxy. We zoomed out to see that our galaxy, the Milky Way, is part of the local group, which is part of the Virgo cluster, which is part of the Virgo supercluster, which is part of Laniakea, a structure spanning over 500 million light-years and containing 100,000 galaxies. And that's our cosmic address. That's where we live in the universe. We're an unimaginably tiny speck on an unimaginably tiny planet in an unimaginably vast cosmos, And we've only just begun to explore the largest objects out there, because as massive as Laniakea is, it's not even close to being the largest structure in the universe. There are galaxies out there that are bigger than you'd think possible. There are black holes so massive they make our sun look like a grain of sand. There are walls and filaments of galaxies stretching across billions of light years, structures so large they challenge our fundamental understanding of how the universe even works. And we're going to dive into all of that in this video. But for now, just take a moment to appreciate the sheer scale of what we've covered so far. From Earth to Laniakea, we've expanded our view by a factor of billions. And we're only just getting started. The universe is so much bigger and stranger than most people realize, and the largest objects within it are about to make everything we've talked about so far seem small by comparison. Galactic giants, planets, stars, and the largest galaxies. So now that we've established our cosmic address and understand just how incomprehensibly vast the structures we're a part of actually are, let's take a step back and focus on some of the individual objects that make up these massive structures. Because while superclusters and galaxy filaments are mind-blowing in their scale, there's something equally fascinating about zooming in and looking at the actual galaxies, stars, and even planets that exist out there in the cosmos. And trust me, some of these individual objects are so absurdly large that they make our entire solar system look like a joke. Let's start with something we can actually wrap our heads around, at least relatively speaking, planets. We've already talked about Earth, which has a diameter of about 12,742 kilometers. That's our home, and to us, it feels massive. But in the grand scheme of things, Earth is actually one of the smaller planets in our solar system. You've got Mars, which is even smaller than Earth, with a diameter of about 6,792 kilometers. Then you've got Venus, which is almost Earth's twin in terms of size, coming in at about 12,104 kilometers. But once you get past the rocky planets and move out to the gas giants, the scale changes dramatically. Jupiter, the largest planet in our solar system, has a diameter of about 139,820 kilometers. That's over 11 times wider than Earth. You could fit over 1,300 Earths inside Jupiter. 1,300. Let that sink in for a second. This single planet is so massive that it contains more than twice the mass of all the other planets in our solar system combined. Jupiter is basically the king of our solar system, second only to the Sun itself in terms of sheer size and gravitational influence. And here's something really interesting about Jupiter that I think puts its scale into perspective. If you were standing on Earth and looked up at Jupiter in the night sky, it's one of the brightest objects you can see with the naked eye. Now imagine if Jupiter was where the Moon is. It would dominate the entire sky. It would be absolutely terrifying, to be honest. The Great Red Spot alone, which is a storm that's been raging on Jupiter for at least 350 years, is bigger than Earth. A storm, bigger than our entire planet, just sitting there, swirling away for centuries. But as massive as Jupiter is, it's actually quite small compared to some of the planets we've discovered orbiting other stars. You've got what are called hot Jupiters, which are gas giants that orbit incredibly close to their host stars. Some of these planets are even larger than Jupiter, with diameters reaching up to 250,000 kilometers or more. There's a planet called HD 100,000b that's about 1.4 times the size of Jupiter, and it orbits its star so closely that its surface temperature is well over 1,000 degrees Celsius. These planets are absolute monsters, and they completely shatter any assumptions we had about how large planets could actually get. But even the largest planets are nothing compared to stars. Stars are where things start to get really interesting, because the size range of stars is absolutely ridiculous. You've got red dwarf stars, which are the smallest and most common type of star in the universe. Red dwarfs have diameters that are typically around 10 to 20% the size of our Sun. Some of them are barely larger than Jupiter. In fact, there's a type of star called a brown dwarf, which is basically a failed star, and these objects can be roughly the same size as Jupiter. They never got quite massive enough to ignite nuclear fusion in their cores, so they just sit there, slowly radiating away their heat over billions of years. They're kind of the sad, pathetic runts of the stellar world, if I'm honest. Then you've got stars like our Sun, which is actually a pretty average star in terms of size. The Sun has a diameter of about 1.4 million kilometers, or about 109 times the diameter of Earth. Again, you could fit over 1 million Earths inside the Sun. The Sun makes up 99.86% of the total mass of our entire solar system. Everything else, all the planets, all the asteroids, all the comets, all of it combined makes up less than 0.2%. The Sun is absolutely dominant in our solar system, and it's not even that big compared to other stars out there, because once you start looking at giant stars and supergiant stars, the scale becomes genuinely difficult to comprehend. Take a star like Betelgeuse, for example. Betelgeuse is a red supergiant located in the constellation Orion, and it's one of the brightest stars visible in the night sky. Betelgeuse has a diameter of roughly 1.4 billion kilometers. That's about 1,000 times larger than the Sun. If you replaced the Sun with Betelgeuse, its surface would extend past the orbit of Mars. It would completely engulf Mercury, Venus, Earth, and Mars. We would all be inside the star. Betelgeuse is so large that despite being about 650 light-years away, we can actually see it as a disk in the sky using advanced telescopes, not just as a point of light. That's how absurdly massive it is. But Betelgeuse isn't even close to being the largest star we know of. You've got stars like VY Canis Majoris, which is a red hypergiant with a diameter estimated to be somewhere around 2 billion kilometers. That's about 1,400 times larger than the Sun. If VY Canis Majoris was in our solar system, its surface would extend past the orbit of Jupiter. You'd have to go all the way out to Saturn before you escaped the star, and even VY Canis Majoris isn't the largest. There's UY Scuti, which for a long time was thought to be the largest known star in the universe. UY Scuti is a red supergiant with a diameter estimated to be around 2.4 billion kilometers, or about 1,700 times the size of the Sun. If you placed UY Scuti at the center of our solar system, its surface would extend past the orbit of Saturn and come close to Uranus. It's so large that it takes light about 8 hours to travel from one side of the star to the other. Light, which moves at 186,000 miles per second, takes 8 hours to cross this single star. Now, there's some debate about which star is actually the largest, because measuring the sizes of these hypergiants is incredibly difficult. They're so far away and so massive that their surfaces are often ill-defined and constantly changing. But one of the current candidates for the largest known star is Stephenson 2-18, which has an estimated diameter of around 3 billion kilometers, or roughly 2,150 times the size of the Sun. If Stephenson 2-18 was placed at the center of our solar system, it would extend beyond the orbit of Saturn and possibly even reach the orbit of Uranus. It's honestly difficult to even conceptualize a star that large. Like, we're talking about a single object that is billions of kilometers across. The numbers are so large that they've lost all meaning at this point. But here's the thing. Even the largest stars are absolutely tiny compared to galaxies. And that's what we're really here to talk about. Because galaxies are collections of billions or even trillions of stars, all bound together by gravity. And the largest galaxies out there are so absurdly massive that they make even the most monstrous stars look like specks of dust. Let's start with a familiar benchmark, the Milky Way. We've already talked about the Milky Way a bit in the previous chapter, but let's dive into it a little more here because it's important to establish a baseline before we start looking at the true galactic giants. The Milky Way is a barred spiral galaxy, which means it has a central bar-shaped structure made of stars with spiral arms extending out from the ends of the bar. It's about 100,000 to 180,000 light-years in diameter, depending on where you measure from, and it contains somewhere between 100 billion and 400 billion stars. That's a huge range, I know, but it's actually really difficult to get an accurate count of all the stars in the galaxy because we're inside it. It's like trying to count all the trees in a forest while you're standing in the middle of it. You can see some of them, but a lot of them are hidden behind other trees. The Milky Way also has a supermassive black hole at its center called Sagittarius A star, which we'll talk more about in the next chapter. But for now, just know that it's there, sitting at the center of the galaxy, with a mass of about 4 million times that of the Sun. It's holding everything together, essentially acting as the gravitational anchor for the entire galaxy. The Milky Way is a pretty standard spiral galaxy. It's not particularly large or particularly small, it's just kind of average, which is actually a good thing for us because it means we're not living in some weird cosmic outlier. We're in a fairly normal galaxy, in a fairly normal part of the universe. But not all galaxies are spiral galaxies like the Milky Way. In fact, some of the largest galaxies in the universe are elliptical galaxies, which look completely different. Elliptical galaxies are basically big, round blobs of stars with no distinct structure. They don't have spiral arms or a central bar. They're just massive collections of stars moving in random orbits around the center of the galaxy. Elliptical galaxies tend to be much older than spiral galaxies, and they're usually formed through the merging of two or more smaller galaxies. When galaxies collide, which happens more often than you'd think, they merge together over the course of hundreds of millions of years, and the end result is often a giant elliptical galaxy. This is actually what's going to happen to the Milky Way and Andromeda when they collide in about 4.5 billion years. Right now, both the Milky Way and Andromeda are spiral galaxies, but when they merge, the resulting galaxy, which again astronomers have nicknamed Milkomeda, is going to be a giant elliptical galaxy. All the stars from both galaxies are going to be mixed together, and the beautiful spiral structure we see now is going to be completely gone. It's going to be a chaotic mess of stars orbiting around a common center, and it's going to be massive. Milkomeda is expected to have a total mass of somewhere around 1 trillion solar masses, making it one of the more massive galaxies in the local universe. But even that pales in comparison to some of the true giants out there. Now, let's talk about some of the largest galaxies we've discovered, because this is where things get truly mind-blowing. The largest galaxies in the universe are almost exclusively elliptical galaxies, and they're absolutely enormous. One of the most famous examples is a galaxy called IC 1101. IC 1101 is located about 1 billion light-years away from us, in the constellation Virgo, and it is, by almost every metric, a monster of a galaxy. IC 1101 has a diameter of somewhere between 4 million and 5.5 million light-years. Let me say that again, 5.5 million light-years across. That is roughly 50 times larger than the Milky Way. 50 times. If you placed IC 1101 where the Milky Way is right now, with its center at the same point as the center of the Milky Way, The edge of IC 1101 would extend well past the Andromeda Galaxy. It would stretch out beyond the local group entirely. It's so large that it's difficult to even comprehend. IC 1101 contains an estimated 100 trillion stars. 100 trillion. For comparison, the Milky Way has somewhere between 100 billion and 400 billion stars. So IC 1101 has at least 250 times more stars than the Milky Way, possibly even more. The total mass of IC 1101 is estimated to be around 2,000 times the mass of the Milky Way. 2,000 times. It's not just a big galaxy, it's a genuinely incomprehensible galaxy. The numbers associated with it are so large that our brains just kind of shut down trying to process them. Now, IC 1101 didn't start out this large. Like all giant elliptical galaxies, it grew to its current size by consuming other galaxies over billions of years. It's basically a cosmic cannibal, sitting at the center of a galaxy cluster called Abell 2029, and over time it's gravitationally captured and merged with countless smaller galaxies that wandered too close. Each time it absorbed another galaxy, it got a little bit bigger, a little bit more massive, until it became the absolute unit of a galaxy that it is today, and it's still growing. There are smaller galaxies in the cluster that are slowly being pulled toward IC 1101, and over the next few billion years they're going to be absorbed as well. IC 1101 is like the Death Star of galaxies, just sitting there, slowly consuming everything around it. But IC 1101 isn't the only giant elliptical galaxy out there. There are quite a few others that are similarly massive. You've got galaxies like a 2261-BCG, which is about 1 million light-years in diameter and contains an estimated 10 trillion stars. What's interesting about a 2261-BCG is that it's unusual for a galaxy of its size because it doesn't seem to have a supermassive black hole at its center, or if it does, it's much smaller than we'd expect. Normally, the more massive a galaxy is, the more massive its central black hole is, but a 2261-BCG seems to break that rule, and astronomers aren't entirely sure why. It's possible that the black hole was ejected from the galaxy during a merger, or maybe it's just hiding somewhere in the galaxy and we haven't found it yet. Either way, it's a bit of a cosmic mystery. Then you've got ESO 444-46, which is about 400,000 light-years in diameter. What makes ESO 444-46 interesting is that it's home to roughly 27,000 star clusters, which is one of the largest populations of star clusters known in any galaxy. Star clusters are dense groups of stars that are all gravitationally bound together, and they're usually found in the outer regions of galaxies. ESO 444-46 has an absolutely ridiculous number of them, which suggests that it's been through multiple rounds of intense star formation over its lifetime. Now, most of the galaxies we've talked about so far have been elliptical galaxies, but there are also some absolutely massive spiral galaxies out there. The largest known spiral galaxy is a galaxy called NGC 6872, also known as the Condor Galaxy. NGC 6872 is located about 212 million light-years away in the constellation Pavo, and it has a diameter of roughly 720,000 light-years. That's about 6 to 7 times larger than the Milky Way, which is absolutely insane for a spiral galaxy. Most spiral galaxies are actually quite a bit smaller than elliptical galaxies, but NGC 6872 is a notable exception. What makes NGC 6872 so large is that it's currently in the process of interacting with another galaxy. It's being stretched and distorted by the gravitational pull of a nearby galaxy called IC 4970, and this interaction has caused NGC 6872 to form these long, extended spiral arms that stretch out for hundreds of thousands of light-years. Eventually, over the course of hundreds of millions of years, NGC 6872 and IC 4970 are going to merge completely, and the resulting galaxy is probably going to be a giant elliptical galaxy. But for now, NGC 6872 holds the title of the largest known spiral galaxy in the universe. There's also a class of galaxies called CD galaxies, which are a specific type of giant elliptical galaxy that forms at the centers of galaxy clusters. CD galaxies can reach diameters of up to 6 million light-years, making them some of the largest individual galaxies in the universe. They're typically about 10 times brighter than the Milky Way and about 100 times more massive. CD galaxies are thought to form through a process called galactic cannibalism, where the central galaxy in a cluster slowly consumes all the smaller galaxies around it over billions of years. It's basically the same process that formed IC 1101, just taken to an even more extreme level. Now, one of the things that's really important to understand about these giant galaxies is that they didn't just form all at once. Galaxies grow over time through a combination of star formation and mergers with other galaxies. When two galaxies of similar size collide, the result is usually a larger elliptical galaxy. When a large galaxy collides with a much smaller galaxy, the smaller galaxy gets absorbed and the larger galaxy grows a bit bigger. This process has been going on for billions of years, and it's how the largest galaxies in the universe got to be so massive. They're not just big, they're old, and they've had billions of years to accumulate mass. In fact, when the Milky Way and Andromeda merge in a few billion years, the resulting galaxy Milkomeda is going to have a total stellar population of around 1 trillion stars, assuming we don't lose too many stars during the merger. That's going to make Milkomeda one of the more massive galaxies in the local universe, though still nowhere near as large as IC 1101 or some of the other true giants. But it's a reminder that galaxies are not static objects. They're constantly evolving, constantly changing, constantly interacting with each other. The universe is a dynamic place, and the galaxies within it are constantly reshaping themselves over cosmic timescales. So, to put all of this into perspective, let's do a quick comparison. Earth is about 12,742 kilometers in diameter. Jupiter is about 139,820 kilometers in diameter. The Sun is about 1.4 million kilometers in diameter. The largest stars, like Stephenson 2-18, are about 3 billion kilometers in diameter. The Milky Way is about 100,000 to 180,000 light-years in diameter. And IC 1101, one of the largest galaxies in the universe, is about 4 to 5.5 million light-years in diameter. We've gone from a planet that's roughly 12,000 kilometers across to a galaxy that's over 5 million light-years across. The scale of the universe is genuinely difficult to comprehend, and we've still got even larger structures to talk about. But before we move on to those even larger structures, there's one more type of object we need to discuss, because while galaxies are massive, there are objects within galaxies that are so dense, so gravitationally powerful, that they warp the very fabric of space and time around them. I'm talking, of course, about black holes. And the largest black holes in the universe are so absurdly massive that they make even the largest stars look like specks of dust. But we'll get to that in the next chapter. Black hole titans, gravity's colossal maw. So, we've talked about the largest galaxies in the universe, these massive collections of hundreds of billions or even trillions of stars, all bound together by gravity. And I mentioned at the end of the last chapter that there are objects within galaxies that are so dense, so gravitationally powerful, that they warp the very fabric of space and time around them. Well, now we need to talk about black holes, because black holes are, without question, some of the most extreme and fascinating objects in the entire universe. And the largest black holes out there are so absurdly massive that they genuinely challenge our understanding of physics and the limits of what should even be possible. Now, before we dive into the truly monstrous supermassive black holes that sit at the centers of galaxies, we need to establish what a black hole actually is, because despite the name, a black hole is not actually a hole. It's not like there's this empty void sitting in space that things fall into. A black hole is a massive concentration of matter that's been compressed into an incredibly tiny space. The gravitational pull of this concentrated mass is so strong that nothing, and I mean nothing, can escape from it once it crosses a certain boundary. Not even light, which is the fastest thing in the universe, can escape. That's why we call them black holes. They don't emit light, they don't reflect light, they just sit there, invisible, warping space and time around them like some kind of cosmic predator. The boundary beyond which nothing can escape is called the event horizon. It's not a physical surface, it's just a point of no return. Once something crosses the event horizon, it's done. It's going to fall toward the center of the black hole, and there's absolutely nothing that can stop it. At the very center of the black hole is what's called the singularity, which is where all the mass of the black hole is concentrated into a point of infinite density. Now, when I say infinite density, I mean that quite literally. All the mass is compressed into a space with zero volume. Our current understanding of physics completely breaks down at the singularity. We don't know what happens there. General relativity and quantum mechanics, the two pillars of modern physics, both fail to describe what's going on at the center of a black hole. It's one of the biggest unsolved problems in all of physics, and it's honestly a bit terrifying when you think about it. There are places in the universe where the laws of physics as we understand them just stop working. Now, black holes form in a few different ways, but the most common way is through the collapse of a massive star. When a star that's at least about 20 times more massive than the Sun reaches the end of its life, it runs out of fuel for nuclear fusion in its core. Without the outward pressure from fusion to counteract gravity, the core collapses in on itself in a fraction of a second. The outer layers of the star explode outward in what's called a supernova, which is one of the most violent and energetic events in the universe. But the core keeps collapsing, and if it's massive enough, it collapses all the way down into a black hole. These are called stellar mass black holes, and they typically have masses ranging from about 3 to a few dozen times the mass of the Sun. The smallest known black hole that we've discovered has a mass of about 3.8 solar masses, and it's paired with a star in a binary system. There's also a black hole called GRS 1915+105, which is one of the fastest spinning black holes we know of. It's rotating at over 1,000 rotations per second. 1,000 rotations per second. That is genuinely difficult to comprehend. The black hole is spinning so fast that it's dragging space and time around with it in a process called frame dragging. If you were somehow able to get close to this black hole without being torn apart by tidal forces, which you can't, you would literally be pulled along by the rotation of space itself. It's like being caught in a whirlpool, except the whirlpool is made of space-time. Stellar mass black holes are fascinating, but they're honestly pretty small compared to what we're really here to talk about. Because at the centers of most galaxies, including our own Milky Way, there exist black holes that are so massive they make stellar mass black holes look like grains of sand. These are called supermassive black holes, and they have masses ranging from millions to billions of times the mass of the Sun, and we're not entirely sure how they form. The prevailing theory is that supermassive black holes grow over time through a combination of two processes. The first process is accretion, which is just a fancy word for eating. A black hole grows by pulling in gas, dust, and even entire stars that wander too close. As matter falls toward the black hole, it forms what's called an accretion disk, which is this swirling disk of superheated material that orbits the black hole before eventually crossing the event horizon. The accretion disk gets incredibly hot, often reaching temperatures of millions of degrees, and it emits enormous amounts of light and radiation across the entire electromagnetic spectrum, from radio waves to X-rays. This is actually how we detect black holes in the first place. We can't see the black hole itself because it doesn't emit light, but we can see the effects it has on the material around it. The second process through which supermassive black holes grow is through mergers. When two galaxies collide and merge, their central supermassive black holes eventually spiral toward each other and merge into an even more massive black hole. This process takes hundreds of millions or even billions of years, but it's a major driver of black hole growth over cosmic timescales, and it's happening all the time throughout the universe. In fact, astronomers have detected gravitational waves from black hole mergers using instruments like LIGO and Virgo. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, and black hole mergers are one of the most powerful sources of gravitational waves in the universe. When two black holes merge, they release more energy in a fraction of a second than all the stars in the observable universe combined. It's honestly one of the most violent and energetic events that can happen in the cosmos. Now, let's talk about the supermassive black hole at the center of our own galaxy, because this is probably the one we understand best simply because it's the closest one to us. The black hole at the center of the Milky Way is called Sagittarius A star, often abbreviated as SCR A star. It has a mass of about 4.3 million times the mass of the Sun, and it's located about 26,000 light-years away from us in the direction of the constellation Sagittarius. Now, 4.3 million solar masses might sound absolutely massive, and it is, but it's actually relatively small for a supermassive black hole. There are supermassive black holes out there that are thousands of times more massive than SCR A star. SCR A star is not particularly active. It's not pulling in a lot of material right now, so it's not generating a huge amount of radiation. But we know it's there because of the effects it has on the stars around it. Astronomers have been tracking the orbits of stars near the center of the galaxy for decades, and what they've found is that these stars are orbiting around an invisible point with an incredibly strong gravitational pull. One star in particular, called S2, orbits SCR A star every 16 years, and at its closest approach, it's moving at nearly 3% the speed of light. 3% the speed of light. That's about 9 million meters per second. The only way a star could be moving that fast is if it's orbiting something incredibly massive and incredibly compact. That's how we know Cerberus star is there, even though we can't see it directly. Well, actually, I say we can't see it directly, but that's not entirely true anymore. In 2019, the Event Horizon Telescope, which is a global network of radio telescopes working together to create an Earth-sized virtual telescope, released the first ever image of a black hole. But it wasn't Cerberus star. It was a black hole at the center of a galaxy called Messier 87, or M87 for short. The black hole in M87 has a mass of about 6 to 6.5 billion times the mass of the Sun, making it over 1,000 times more massive than SCR A star. The image showed the shadow of the black hole against the glowing accretion disk surrounding it. and it was one of the most important astronomical observations of the 21st century. It confirmed what we'd theorized for decades, that black holes exist, that they have event horizons, and that general relativity accurately describes their behavior. Then, in 2022, the Event Horizon Telescope released an image of Scurry star, the black hole at the center of our own galaxy, and it looked remarkably similar to the image of the M87 black hole, just smaller. The shadow of Scurry star has a diameter that spans about half the width of Mercury's orbit around the Sun. That might not sound that big, but remember, this is the shadow, not the black hole itself. The actual event horizon of Scurry star is much smaller, with a diameter of only about 24 million kilometers. That's tiny compared to the size of the galaxy, but it's still about 17 times larger than the Sun. The discovery and imaging of these black holes earned the Nobel Prize in Physics in 2020, and it's been a huge step forward in our understanding of these extreme objects. As of now, the Event Horizon Telescope has confirmed the existence of over 100 supermassive black holes in various galaxies throughout the universe. And the thing is, we think most large galaxies have a supermassive black hole at their center. It's basically a standard feature of galaxies at this point. The Milky Way has one, Andromeda has one, M87 has one, and so on. But Scurry star and the M87 black hole are relatively small compared to some of the true monster black holes out there. Let's talk about some of the largest supermassive black holes we've discovered, because the scale of these objects is genuinely mind-blowing. There's a black hole called OJ287, located in a galaxy about 3.5 billion light-years away, and it has a mass of about 18 billion times the mass of the Sun. 18 billion, that's over 4,000 times more massive than Scurry star. And here's something really interesting about OJ287. It's actually part of a binary black hole system. There's a smaller black hole, though smaller is relative here because it's still about 40 times more massive than Scurry star, orbiting around the larger one. These two black holes are locked in a death spiral, and eventually, over the course of millions of years, they're going to merge into an even more massive black hole. Then you've got a pair of black holes in a galaxy called NGC 7727. One of them has a mass of about 6 million solar masses, and the other has a mass of about 150 million solar masses. These two black holes are only about 1,600 light-years apart, which is incredibly close on galactic scales, and they're expected to merge within the next 250 million years. When they do merge, the resulting black hole is going to have a mass of about 156 million solar masses, and it's going to release an absolutely enormous amount of energy in the form of gravitational waves. There's also a black hole in a system called the Cosmic Horseshoe, which was detected through a process called gravitational lensing. Gravitational lensing is when the gravity of a massive object bends the light from objects behind it, creating a distorted or magnified image. In this case, the black hole in the Cosmic Horseshoe has a mass of about 36 billion solar masses, making it one of the most massive black holes ever discovered. What's interesting about this black hole is that it's dormant. It's not actively pulling in material, so it's not generating a lot of radiation. It's just sitting there, quietly warping space-time around it. Thomas Collett, an astronomer at the University of Portsmouth, said about this discovery, "This is amongst the top 10 most massive black holes ever discovered, and quite possibly the most massive." The fact that we can detect dormant black holes like this one is actually a huge deal. Most of the supermassive black holes we discover are active, meaning they're pulling in material and generating radiation that we can detect. But dormant black holes are much harder to find because they're not emitting anything. The only way we can detect them is through their gravitational effects on the surrounding space and time. Carlos Mello, one of the lead researchers on the study that discovered the cosmic horseshoe black hole, said that this method allows astronomers to detect hidden ultramassive black holes across the universe, even when they are completely silent. This is incredibly important because it means there could be many more massive black holes out there that we simply haven't detected yet because they're not active. But even the cosmic horseshoe black hole isn't the largest black hole we know of. That title goes to a black hole called TON 618, and this thing is an absolute monster. TON 618 is a quasar, which is an extremely luminous active galactic nucleus powered by a supermassive black hole. The black hole in TON 618 has a mass of about 66 billion times the mass of the Sun. 66 billion. Let me put that into perspective for you. Our Sun has a mass of about 2 × 10 to the power of 30 kilograms. TON 618 has a mass of about 1.32 × 10 to the power of 41 kilograms. That is so large that it's difficult to even comprehend. If you were to replace the Sun with TON 618, the event horizon of this black hole would extend out to about 14.7 billion kilometers. That's roughly halfway to the edge of our solar system. You could fit about 11 solar systems side by side inside the event horizon of TON 618. 11 solar systems. This black hole is so large that it genuinely shouldn't even exist, according to some theoretical models. Back in 2015, an astrophysicist named Andrew King calculated that there should be a theoretical maximum size for non-spinning black holes, and he came up with a number of about 50 billion solar masses. The idea is that once a black hole gets that large, the radiation pressure from the accretion disk should prevent any more material from falling in, effectively capping the black hole's growth. But TON 618 exceeds that limit. It's 66 billion solar masses, which is 32% larger than the theoretical maximum. So either our models are wrong, or there's something unusual about TON 618 that allowed it to grow beyond what should be possible. Now here's something really important to understand about TON 618. We're not seeing it as it is right now. We're seeing it as it was 10 billion years ago. TON 618 is so far away that the light we're seeing from it left the black hole 10 billion years ago, long before our Sun or Earth even existed. So what we're observing is this black hole as it existed in the early universe, when galaxies and black holes were still in the process of forming and growing. It's entirely possible that TON 618 has grown even larger in the 10 billion years since the light we're seeing left it. Or maybe it's merged with another black hole by now. We have no way of knowing what the current state of TON 618 is, because the light showing us that state won't reach us for another 10 billion years. TON 618 is what's called an ultramassive black hole, which is a classification reserved for black holes with masses greater than 10 billion solar masses. These objects are extremely rare, and we've only discovered a handful of them. The reason they're so rare is probably related to the theoretical maximum size issue I mentioned earlier. Most black holes simply can't grow large enough to reach ultramassive status because the radiation pressure from their accretion disks prevents further growth. But the ones that do exist are absolute cosmic titans, and they're some of the most extreme objects in the entire universe. One of the reasons TON 618 is so bright, and how we even detected it in the first place, is because it's an active quasar. Quasars are powered by supermassive black holes that are actively pulling in enormous amounts of material. As that material falls toward the black hole, it heats up and emits light across the entire electromagnetic spectrum, from radio waves to X-rays. Quasars are some of the brightest objects in the universe, often outshining entire galaxies. TON 618 shines with the light of thousands of galaxies combined. It's so bright that we can see it from 10 billion light-years away, despite the fact that it's just a single object, not a collection of billions of stars like a galaxy. The accretion disk around TON 618 is absolutely massive. We're talking about a disk of superheated gas and dust that's hundreds of billions of kilometers across, swirling around the black hole at a significant fraction of the speed of light. The temperatures in the inner regions of the accretion disk are millions of degrees, hot enough to strip electrons from atoms and create a plasma. This plasma emits intense radiation, and it's this radiation that makes quasars so bright. But here's the thing. For every bit of matter that falls into the black hole, a significant fraction of its mass energy is converted into radiation through the process described by Einstein's famous equation, E equals mc squared. This means that TON 618 is not only the most massive black hole we know of, but it's also one of the most energetic objects in the universe. Now, Jeremy Schnittman, a theorist at NASA, said something really interesting about our observations of supermassive black holes. He said, "Direct measurements confirm the presence of more than 100 supermassive black holes. The key word there is direct. We've directly observed and confirmed the existence of over 100 supermassive black holes using various techniques, from tracking the orbits of stars around them, to imaging their event horizons with the Event Horizon Telescope, to detecting them through gravitational lensing. But the thing is, we think there are billions of supermassive black holes out there in the universe, one in the center of nearly every large galaxy. We just haven't been able to observe most of them yet because they're either too far away or too faint. The fact that we've confirmed over 100 of them is actually a huge achievement, and it's only going to get better as our telescopes and detection methods improve. Supermassive black holes play a crucial role in the evolution of galaxies. They influence star formation in the galactic core. They regulate the amount of gas available for new stars to form, and they can even trigger bursts of star formation through their interactions with the surrounding gas. When a supermassive black hole is active and pulling in material, the energy released by the accretion disk can heat up the surrounding gas and blow it away from the galaxy, effectively shutting down star formation in the core. This is called feedback, and it's one of the main ways that supermassive black holes regulate the growth of their host galaxies. Without supermassive black holes, galaxies would look very different than they do today. So, to summarize, black holes are among the most extreme objects in the universe. They're regions of space where gravity is so strong that nothing, not even light, can escape. They range in size from stellar mass black holes, which are a few times more massive than the Sun, to supermassive black holes, which are millions or even billions of times more massive. The largest black hole we know of, TON 618, has a mass of 66 billion solar masses and an event horizon that could contain 11 solar systems side by side. These objects shouldn't even be possible according to some theoretical models, and yet they exist, sitting at the centers of galaxies, warping space and time around them, and fundamentally shaping the evolution of the universe. But as massive as TON 618 is, and as incomprehensibly large as these supermassive black holes are, they're still individual objects. They're still just single points of concentrated mass sitting at the centers of galaxies. If we really want to understand the largest structures in the universe, we need to zoom out even further and start looking at collections of galaxies. Because the largest structures in the universe aren't individual objects like black holes or galaxies. They're massive clusters and superclusters and walls of galaxies stretching across hundreds of millions or even billions of light years. And that's exactly what we're going to dive into next. So we've talked about individual galaxies, we've talked about supermassive black holes that sit at the centers of those galaxies, and we've established just how absurdly massive these objects can get. But here's the thing, galaxies don't just float around in space all by themselves like lonely islands. They hang out together. They cluster. And when I say cluster, I'm not talking about a few dozen galaxies chilling in the same general area. I'm talking about hundreds or even thousands of galaxies all bound together by gravity, forming structures so massive that they're among the largest gravitationally bound objects in the entire universe. These are galaxy clusters, and they're what we're going to dive into in this chapter. Because if you thought individual galaxies were big, wait until you see what happens when you put 1,000 of them in the same place. Now, before we get into the truly massive galaxy clusters out there, structures like the Phoenix cluster, which we'll absolutely get to, we need to understand the cosmic hierarchy that leads to these structures forming in the first place. Because the universe is organized in a very specific way, almost like a pyramid of ever larger structures stacked on top of each other. At the bottom of the pyramid, you've got individual galaxies like the Milky Way. Then you've got galaxy groups, which are collections of tens to a few hundred galaxies all gravitationally bound together. We talked about the local group in the first chapter, which contains the Milky Way, Andromeda, and about 50 smaller galaxies. That's a galaxy group. Above galaxy groups, you've got galaxy clusters, which are much larger. Galaxy clusters contain hundreds to thousands of galaxies, and they span several million light-years across. These are the largest structures in the universe that are still fully bound by gravity. What that means is that the galaxies within a cluster are all held together by their mutual gravitational attraction, and despite the expansion of the universe trying to pull everything apart, gravity wins. The galaxies in a cluster aren't going anywhere, they're stuck together for the long haul. Then, above galaxy clusters, you've got superclusters, which are collections of galaxy clusters and groups spanning hundreds of millions of light-years. We talked about Laniakea in the first chapter, which is the supercluster we're a part of. But here's the key distinction: superclusters are not gravitationally bound. The expansion of the universe is too strong at those scales, so while we can identify superclusters as regions of space with a higher than average density of galaxies, they're not stable structures. Over billions of years, they're going to be pulled apart by the expansion of space. Galaxy clusters, on the other hand, are stable. They're the top of the pyramid when it comes to gravitationally bound structures. Beyond that, the universe's expansion takes over. So galaxy clusters are where gravity makes its final stand against the expansion of the universe, and they're absolutely massive. The typical galaxy cluster has a mass of somewhere between 10 to the power of 14 and 10 to the power of 15 solar masses. That's 100 trillion to a quadrillion times the mass of the Sun. Let me say that again. A quadrillion times the mass of the Sun. These structures are so massive that they genuinely warp spacetime around them to a degree that we can actually observe. When light from distant galaxies passes through or near a galaxy cluster, the cluster's gravity bends the light, creating distorted or magnified images of those background galaxies. This effect is called gravitational lensing, and it's one of the main ways we detect and study galaxy clusters. The more massive the cluster, the more it bends light. Some of the most massive clusters act like cosmic magnifying glasses, allowing us to see galaxies that would otherwise be too faint or too far away to observe. Now, here's something really important about galaxy clusters that you need to understand if you want to wrap your head around how these structures exist in the first place. Most of the mass in a galaxy cluster is not in the galaxies themselves. It's not even in the gas that fills the space between the galaxies. Most of the mass is dark matter. We touched on dark matter briefly in the first chapter, but it's absolutely crucial here, so let's dive into it a bit more. Dark matter is this mysterious substance that we can't see, we can't detect directly, but we know it's there because of its gravitational effects. It makes up about 85% of all the matter in the universe, and in galaxy clusters that percentage is even higher. Roughly 80 to 90% of the total mass of a galaxy cluster is dark matter. If you just looked at the visible galaxies in a cluster, if you added up all the stars and all the planets and all the gas that you can actually see, you'd come up with a number that's nowhere near enough mass to hold the cluster together. The galaxies are moving so fast, often at speeds of hundreds or even thousands of kilometers per second, that they should just fly apart. The visible matter alone doesn't have enough gravity to keep them bound, but they don't fly apart. And the reason they don't is because there's this massive halo of dark matter surrounding the cluster, providing the gravitational glue that keeps everything together. We don't know what dark matter is made of. That's one of the biggest unsolved mysteries in all of physics. We've got some theories, particles called WIMPs, which stands for weakly interacting massive particles, or axions, or sterile neutrinos. But we haven't detected any of these particles directly yet. What we do know is that dark matter interacts with ordinary matter only through gravity. It doesn't emit light, it doesn't absorb light, it doesn't interact with the electromagnetic force at all as far as we can tell. It's completely invisible, but it's there, and it's absolutely essential to the existence of galaxy clusters. Without dark matter, these massive structures simply couldn't exist. Now, the second largest component of mass in a galaxy cluster is something called the intracluster medium, or ICM. The intracluster medium is this hot, diffuse gas that fills the space between the galaxies in a cluster. And when I say hot, I mean hot. This gas has temperatures of tens of millions of degrees Kelvin, sometimes even over 100 million degrees. At those temperatures, the gas is completely ionized, meaning the electrons have been stripped away from the atoms, creating a plasma. This plasma is so hot that it emits X-rays, and in fact, that's one of the main ways we detect galaxy clusters in the first place. We point X-ray telescopes like Chandra at regions of space, and if there's a galaxy cluster there, we see this diffuse glow of X-rays coming from the intracluster medium. The intracluster medium makes up about 10 to 15% of the total mass of a galaxy cluster, which is actually more mass than all the stars in all the galaxies in the cluster combined. Let me say that again. There is more mass in the hot gas filling the space between the galaxies than there is in the galaxies themselves. The galaxies, which are these massive collections of hundreds of billions of stars, make up only about 1 to 5% of the total mass of the cluster. The rest is dark matter and hot gas. It's honestly kind of wild when you think about it. The things we can see, the galaxies, are just a tiny fraction of what's actually there. So you've got dark matter providing the gravitational scaffolding, you've got the intracluster medium filling the space between galaxies, and you've got the galaxies themselves. These three components all interact with each other in really interesting ways. When galaxies move through the intracluster medium, they experience what's called ram pressure, which is basically a drag force caused by the hot gas. This ram pressure can strip gas away from the galaxies, a process called ram pressure stripping, which can affect star formation within those galaxies. The hot intracluster medium can also interact with the supermassive black holes at the centers of galaxies, creating these massive bubbles of hot gas that rise up through the cluster. It's a really dynamic environment, and it's constantly changing over time. Now, galaxy clusters don't exist in isolation either. They're connected to each other and to other large-scale structures through what's called the cosmic web. The cosmic web is this massive web-like structure of dark matter and gas that spans the entire observable universe. It's made up of filaments, which are these long thread-like structures of galaxies and dark matter that connect clusters and superclusters over hundreds of millions of light years. Between the filaments, you've got voids, which are vast, empty regions of space with very few galaxies. The cosmic web is the largest scale structure in the universe, and it's the result of how matter has clumped together over the past 13.8 billion years since the Big Bang. In the early universe, matter was distributed almost uniformly. There were tiny fluctuations in density, but they were incredibly small, on the order of 1 part in 100,000. But over time, gravity amplified those tiny fluctuations. Regions that were slightly denser than average pulled in more matter, becoming even denser, while regions that were slightly less dense lost matter and became voids. This process continued for billions of years, and the end result is the cosmic web we see today. The densest regions of the cosmic web are where galaxy clusters form. They sit at the intersections of filaments, like knots in a web, and they're constantly pulling in more matter from the surrounding filaments, growing larger over time. The cosmic web is one of the most beautiful structures in nature, to be honest. If you could somehow see the entire observable universe at once, with all the galaxies and all the dark matter visible, you'd see this intricate web of filaments and voids stretching out in every direction. It's honestly stunning, and it's a reminder that the universe has structure on every scale, from planets to stars to galaxies to clusters to the cosmic web itself. All right, so now that we've established what galaxy clusters are and how they fit into the larger cosmic hierarchy, let's talk about one of the most extreme galaxy clusters we've ever discovered. This thing is an absolute monster, and it's called the Phoenix Cluster. The Phoenix Cluster, officially designated SPT-CLJ 2344-4243, which is a mouthful, so we're just going to call it Phoenix, is one of the most massive and most X-ray luminous galaxy clusters known to exist. It was discovered by the South Pole Telescope, which is a radio telescope located at the Amundsen-Scott South Pole Station in Antarctica. The cluster is located about 5.7 billion light-years away from us in the southern constellation Phoenix, which is where it gets its name. Now, when I say Phoenix is massive, I mean it's genuinely one of the most massive galaxy clusters we've ever found. The total mass of the Phoenix cluster is estimated to be somewhere around 2 to 3 times 10 to the power of 15 solar masses. That's 2 to 3 quadrillion times the mass of the Sun. To put that into perspective, that's about the same mass as 2 to 3 million Milky Way galaxies, 2 to 3 million galaxies worth of mass, all concentrated into a region of space that's only a few million light-years across. The numbers are so large that they've completely lost all meaning at this point. But we're going to keep going anyway. Phoenix is not just massive in terms of its total mass, it's also incredibly luminous in X-rays. In fact, it's one of the most powerful X-ray sources in the entire sky. The X-ray luminosity of Phoenix is about 10 times higher than what you'd expect for a cluster of its mass. Most galaxy clusters emit X-rays from their hot intracluster medium, and the amount of X-rays they emit is usually proportional to their mass. But Phoenix is off the charts. It's emitting far more X-rays than it should, and the reason for that has to do with what's happening at the center of the cluster. At the heart of the Phoenix cluster is a massive central galaxy, and that galaxy is undergoing an absolutely extreme burst of star formation. We're talking about a star formation rate of somewhere between 600 and 800 solar masses per year. 600 to 800 solar masses per year. Let me put that into perspective for you. Our Milky Way forms new stars at a rate of about 1 to 3 solar masses per year. That's pretty typical for a galaxy like ours. The Phoenix cluster's central galaxy is forming stars at a rate that's 200 to 800 times higher than the Milky Way. It's an absolute star formation factory, and it's one of the highest star formation rates ever observed in a galaxy cluster. Now, the reason this is happening has to do with something called a cooling flow. In most galaxy clusters, the hot intracluster medium is in a state of equilibrium. The gas is heated by various processes, including shocks from galaxy mergers and energy injected by supermassive black holes, and it cools through the emission of X-rays. Normally, these heating and cooling processes balance each other out, and the temperature of the gas stays relatively constant. But in the Phoenix cluster, something different is happening. The gas at the center of the cluster is cooling down much faster than it's being heated. It's going from temperatures of around 100 million degrees Kelvin down to around 10,000 degrees Kelvin. When the gas cools that much, it can no longer support itself against gravity, so it collapses down onto the central galaxy, where it fuels this intense burst of star formation. Cooling flows were predicted by theory decades ago, but for a long time we didn't observe them in the way we expected. The problem was that in most galaxy clusters, there's a supermassive black hole at the center of the central galaxy, and that black hole is active. It's pulling in material and generating jets of plasma that shoot out from the poles of the black hole at close to the speed of light. These jets inject enormous amounts of energy into the surrounding gas, heating it up and preventing it from cooling. This process is called AGN feedback, where AGN stands for active galactic nucleus. AGN feedback is one of the main reasons why we don't see stronger cooling flows in most galaxy clusters. The black hole essentially acts as a thermostat, regulating the temperature of the gas and preventing it from cooling too much. But in the Phoenix cluster, the cooling flow is so strong that even the AGN feedback can't fully suppress it. There is a supermassive black hole at the center of the Phoenix cluster's central galaxy, and it is active. It's generating jets and bubbles of hot plasma, and those jets are injecting energy into the surrounding gas. But the cooling is happening so fast that the AGN feedback can't keep up. The gas is cooling faster than the black hole can heat it, and as a result, you've got this massive inflow of cold gas onto the central galaxy, fueling the intense star formation we observe. This is actually a really big deal from a theoretical standpoint. For a long time, astronomers thought that AGN feedback alone would be enough to prevent strong cooling flows in galaxy clusters. The idea was that the black hole would always be able to regulate the temperature of the gas and prevent it from cooling too much. But the Phoenix cluster shows us that's not always the case. There are conditions under which the cooling can overpower the feedback, and when that happens, you get these extreme bursts of star formation. Phoenix is a key testbed for understanding how galaxy clusters evolve over time and how the balance between cooling and feedback changes as clusters age. The Phoenix cluster has been studied extensively using a variety of telescopes and instruments. The Chandra X Ray Observatory has been crucial for mapping out the X-ray emission from the intracluster medium and measuring the temperature and density of the gas. The Hubble Space Telescope has been used to study the central galaxy and the star formation happening within it. Ground-based telescopes have measured the velocities of galaxies within the cluster, allowing us to estimate the total mass of the cluster using what's called the virial theorem, which relates the kinetic energy of the galaxies to the gravitational potential energy of the cluster. All of these observations have come together to give us a detailed picture of what's happening in Phoenix, and it's one of the most extreme and fascinating galaxy clusters we've ever discovered. Now, Phoenix is not the only massive galaxy cluster out there. There are quite a few others that are similarly extreme. You've got clusters like El Gordo, which is Spanish for the fat one, and it's one of the most massive clusters known at the redshift it's located at. El Gordo has a mass of about 3 × 10⁻15 solar masses, making it comparable to Phoenix in terms of total mass. There's also the Bullet Cluster, which is famous for providing some of the best evidence for dark matter. The Bullet Cluster is actually two galaxy clusters that collided with each other, and when they collided, the hot gas from each cluster interacted and slowed down, but the dark matter passed right through without interacting. By mapping out the distribution of mass using gravitational lensing and comparing it to the distribution of hot gas using X-ray observations, astronomers were able to show that most of the mass is not where the gas is, providing strong evidence that dark matter exists. There's also the Coma cluster, which is one of the closest large galaxy clusters to us at a distance of about 320 million light-years. The Coma cluster contains over 1,000 galaxies and has a total mass of about 10 to the power of 15 solar masses. It was actually the study of the Coma cluster back in the 1930s that provided some of the first evidence for dark matter. An astronomer named Fritz Zwicky measured the velocities of galaxies in the Coma cluster and realized that they were moving way too fast for the visible matter in the cluster to hold them together. He proposed that there must be some kind of unseen matter, which he called dark matter, providing the extra gravity needed to keep the cluster bound. It took decades before his idea was widely accepted, but today we know that he was absolutely right. Galaxy clusters like Phoenix, El Gordo, the Bullet Cluster, and the Coma cluster are all part of the same cosmic web of filaments and voids that spans the entire observable universe. They sit at the densest nodes of the cosmic web, where filaments intersect, and they're constantly growing by pulling in more matter from the surrounding filaments. Over time, as the universe continues to expand and evolve, these clusters will continue to grow, merging with other clusters and pulling in more galaxies from the cosmic web. But here's the thing. Galaxy clusters are as large as gravitationally bound structures get. Beyond the scale of galaxy clusters, the expansion of the universe dominates, and structures are no longer stable. Superclusters like Laniakea are not gravitationally bound, and over billions of years they're going to be pulled apart by the expansion of space driven by dark energy. There's even a quote that sums this up pretty well, and it goes something like this. The largest structures that are bound by gravity are clusters of galaxies. Beyond that, the expansion of the universe wins. That's the reality of the cosmos we live in. Gravity can only hold things together up to a certain scale, and once you go beyond that scale, dark energy takes over. But even though superclusters and larger structures aren't gravitationally bound, they still exist as observable structures in the universe. And some of these structures are so large, so massive, that they genuinely challenge our understanding of how the universe should be organized. There are walls and filaments of galaxies stretching across billions of light-years, structures so large that according to the cosmological principle, which states that the universe should look the same in all directions on large enough scales, they shouldn't even exist. But they do exist, and that's what we're going to dive into in the next chapter. Because if you thought galaxy clusters were massive, wait until you see the walls and filaments that connect them across the cosmos. These are structures that push the limits of what our current theories can explain, and they're some of the most mysterious and fascinating objects in the entire universe. The universe's forbidden walls, challenging the cosmological principle. So, we've established that galaxy clusters are the largest gravitationally bound structures in the universe. Phoenix, El Gordo, the Coma cluster, these are the titans of the cosmos. Massive collections of hundreds or thousands of galaxies, all held together by gravity, defying the expansion of the universe through sheer gravitational might. And we've talked about how beyond the scale of galaxy clusters, dark energy wins. The expansion of space takes over, and structures can no longer stay bound together. Superclusters like Laniakea exist as observable regions of higher than average galaxy density, but they're not stable. Over billions of years, they're going to be pulled apart by the expansion of space. That's the reality of the universe we live in. Gravity can only hold things together up to a certain scale, and once you go beyond that scale, the universe's expansion dominates. But here's where things get really interesting, and honestly a bit unsettling from a theoretical standpoint. Even though structures beyond galaxy clusters aren't gravitationally bound, they still exist as observable features in the universe. We can map them, we can study them, we can see how galaxies are distributed across cosmic scales. And when we do that, when we zoom out and look at the largest scales possible, we see something that, according to our fundamental understanding of cosmology, we shouldn't be seeing. We see structures so large, so massive, that they genuinely challenge one of the core principles upon which modern cosmology is built. I'm talking about the cosmological principle, and I'm talking about structures that seem to violate it. These are the universe's forbidden walls, and they're some of the most mysterious and controversial objects in all of astronomy. Now, before we can understand why these massive structures are so controversial, we need to understand what the cosmological principle actually is. Because this is one of those foundational concepts in cosmology that underpins pretty much everything we think we know about the universe. The cosmological principle states that the universe is homogeneous and isotropic on large enough scales. Homogeneous means that the universe looks the same no matter where you are. If you were to pick a random spot in the universe and measure the average density of matter, and then pick another spot a few billion light years away and measure the density there, you'd get roughly the same answer. Isotropic means that the universe looks the same in all directions. If you look north, and then you look south, and then you look east and west, you'd see roughly the same distribution of galaxies and matter in every direction. The universe has no preferred location and no preferred direction. It's the same everywhere and in every direction, at least on large enough scales. Now, you might be thinking, hang on a second, we just spent the last few chapters talking about how the universe is incredibly structured. We've got planets, stars, galaxies, galaxy clusters, superclusters, filaments, voids. How can the universe be homogeneous and isotropic when there's so much structure? And that's a great question. The key phrase here is on large enough scales. On small scales, the universe is absolutely not homogeneous. Earth is way denser than the space around it. Our solar system is denser than interstellar space. The Milky Way is denser than the space between galaxies. Galaxy clusters are denser than the voids between them. There's structure everywhere you look on small scales, but the cosmological principle doesn't apply to small scales. It applies to large scales, scales of hundreds of millions of light years or more. And the question is, what counts as a large enough scale for the universe to start looking homogeneous and isotropic? The general consensus among cosmologists, based on both theory and observations, is that the universe should start to look homogeneous and isotropic once you're looking at scales of around 300 to 400 million light-years or larger. At those scales, if you divide the universe up into big cubes that are each a few hundred million light-years on a side, each cube should have roughly the same number of galaxies, roughly the same amount of matter, roughly the same average density. There might be some variation from cube to cube, but the variation should be small, on the order of a few % at most. And if you zoom out even further, to scales of 1 billion light-years or more, the universe should look even more uniform. The variations should smooth out even more. That's what the cosmological principle predicts, and for the most part, observations support this. When we look at the cosmic microwave background, which is the afterglow of the Big Bang, we see that it's incredibly uniform. The temperature of the cosmic microwave background is almost exactly the same in every direction, with variations of only about 1 part in 100,000. That's an incredibly high level of uniformity, and it's strong evidence that the early universe was very homogeneous and isotropic. And when we map out the distribution of galaxies in the nearby universe, we find that on scales of a few 100 million light-years, things do start to average out. You've got filaments and voids, sure, but when you take a big enough volume of space, the average density is pretty consistent from one region to another. The cosmological principle is not just some arbitrary assumption that cosmologists came up with because it makes the math easier, although it definitely does make the math easier. It's actually based on a pretty fundamental idea that goes back to the Copernican principle, which states that we don't occupy a special place in the universe. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The Milky Way is not the center of the universe. We're not special. We're just observers sitting at some random location in a vast cosmos. And because we're not special, the universe we see from our location should be pretty much the same as the universe you'd see from any other location. That's the essence of the cosmological principle. It's a statement about our place in the universe, or rather, our lack of a special place. The cosmological principle is also deeply embedded in the standard model of cosmology, which is called the lambda CDM model. Lambda stands for the cosmological constant, which is basically another name for dark energy, and CDM stands for cold dark matter. The lambda CDM model is our best current theory for how the universe has evolved from the Big Bang to the present day. It describes how matter clumped together over time to form galaxies and larger structures, how the universe has expanded and continues to expand, and how dark energy is causing that expansion to accelerate. And one of the key assumptions baked into the lambda CDM model is the cosmological principle. The model assumes that the universe is homogeneous and isotropic on large scales, and it uses that assumption to make predictions about what we should observe when we look out into the cosmos. One of those predictions is that there should be a maximum size for structures in the universe. Because if the universe is truly homogeneous on large enough scales, then you shouldn't be able to have structures that are so large they span a significant fraction of the observable universe. There has to be a cutoff, a scale beyond which structures simply don't exist because the universe is too uniform. And based on the lambda CDM model and the cosmological principle, that cutoff should be somewhere around 1.2 to 1.5 billion light-years. Structures larger than that shouldn't exist, or at the very least, they should be extremely rare and only marginally larger than the cutoff. Anything significantly larger than 1.5 billion light-years would be a problem for the cosmological principle because it would suggest that the universe is not as homogeneous as we think it is. So, you can probably see where this is going, because astronomers have discovered structures that are way larger than 1.5 billion light-years. We're talking about structures that are multiple billions of light-years across. Structures so large that their very existence seems to contradict the cosmological principle, and that's a big deal. That's not just some minor discrepancy that can be explained away with a bit of tweaking to the models. If these structures are real, and if they're as large as they appear to be, then we might need to seriously reconsider some of our most fundamental assumptions about the universe. Now, before we dive into the specifics of these massive structures, I want to talk about how we even detect them in the first place. Because it's not like we can just look up at the night sky and see a giant wall of galaxies stretching across billions of light-years. Most of these structures are so far away that the individual galaxies within them are incredibly faint, and it takes sophisticated telescopes and surveys to map them out. One of the key tools astronomers use to study large-scale structures in the distant universe is something called a quasar. Quasars are some of the most luminous objects in the entire universe. They're powered by supermassive black holes that are actively pulling in enormous amounts of material, and as that material falls toward the black hole, it heats up and emits light across the entire electromagnetic spectrum. A single quasar can outshine an entire galaxy, and because they're so bright, we can see them from incredibly far away. Some of the most distant quasars we've observed are over 13 billion light-years away, meaning we're seeing them as they were when the universe was less than 1 billion years old. Quasars are like cosmic lighthouses, beacons shining across the universe, and they allow us to map out the distribution of matter in the distant universe in a way that wouldn't be possible with normal galaxies, which are just too faint to see at those distances. Quasars tend to be found in regions of higher than average density. They form in massive galaxies that are undergoing intense bursts of activity, and those massive galaxies tend to be located in the denser regions of the cosmic web, in places where filaments intersect and matter is clumped together. So, if you find a bunch of quasars clustered together in the same region of space, it's a pretty good bet that there's a large-scale structure there, a region of higher than average density that could be a protocluster or a forming supercluster or something along those lines. Astronomers have used this technique to map out large-scale structures in the distant universe, looking for groupings of quasars that might indicate the presence of massive structures. And that brings us to one of the most controversial discoveries in modern cosmology. In 2013, a team of astronomers led by Roger Clouse announced the discovery of something they called the Huge Large Quasar Group, or Huge-LQG for short. The Huge-LQG is a grouping of 73 quasars located about 9 billion light-years away from us. Now, 73 quasars might not sound like a huge number, but the thing that makes the Huge-LQG so remarkable is its size. The structure spans approximately 4 billion light-years across. 4 billion light-years. Let me say that again because I want to make sure it sinks in. This structure is 4 billion light-years from one end to the other. That is nearly 3 times larger than the theoretical maximum size predicted by the cosmological principle and the lambda CDM model. 4 billion light-years is so large that it's genuinely difficult to comprehend. Light, which moves at 186,000 miles per second, takes 4 billion years to cross this structure. Our entire observable universe is only about 93 billion light-years across, and that's measured from edge to edge, accounting for the expansion of space over the past 13.8 billion years. The Huge-LQG spans roughly 4% of the diameter of the observable universe. It's absolutely enormous, and according to the standard model of cosmology, it shouldn't exist. When the discovery of the Huge-LQG was announced, it sent shockwaves through the astronomical community. Roger Clouse, the lead researcher, said at the time, "While it is difficult to fathom the scale of this large quasar group, we can say quite definitely it is the largest structure ever seen in the entire universe." The discovery was published in the journal Monthly Notices of the Royal Astronomical Society, and it immediately sparked a heated debate. Some astronomers hailed it as evidence that the cosmological principle might not be as ironclad as we thought. Others were more skeptical, arguing that the structure might not be as coherent as it appeared, or that it might just be a statistical fluke, a random clustering of quasars that looks like a structure but isn't actually gravitationally connected in any meaningful way. The problem with determining whether the Huge-LQG is a real coherent structure or just a random grouping comes down to how we define a structure in the first place. Unlike galaxy clusters, which are gravitationally bound and clearly defined, large quasar groups are much more ambiguous. The quasars are spread out over such a large volume of space that they're definitely not gravitationally bound to each other. They're not all part of a single, unified system in the same way that the galaxies in a galaxy cluster are. Instead, what we're looking at is a region of space where the density of quasars is higher than average. The question is that higher density significant enough to call it a structure, or is it just noise in the data? Some astronomers have argued that the Huge-LQG is not a real structure, that it's just a chance alignment of quasars that happen to be located in the same general region of space when viewed from Earth. If you take a large enough volume of the universe and look for patterns, you're going to find patterns just by random chance. It's like looking at clouds and seeing shapes. The shapes aren't really there, they're just the result of random variations that your brain interprets as meaningful. The same thing could be happening with the Huge-LQG. Maybe it's just a random fluctuation in the density of quasars and we're reading too much into it. But other astronomers, including Roger Close and his team, argue that the Huge-LQG is statistically significant. They've done the calculations, they've run the simulations, and they've determined that the probability of seeing a grouping of quasars this large by random chance is incredibly small. The structure is just too big and too dense to be a fluke. And if it's not a fluke, then it's a real structure, and that means the cosmological principle has a problem. Because a structure this large should not exist in a universe that's truly homogeneous on scales of a few 100 million light-years. The debate over the Huge-LQG has been going on for over a decade now, and it's still not fully resolved. There have been follow-up studies, some of which support the existence of the structure, and others which cast doubt on it. But the Huge-LQG is not the only massive structure that's been discovered. There are others, and some of them are even larger. And that's what makes this whole situation so intriguing, because if it was just one structure, you could maybe write it off as an anomaly or a statistical outlier. But when you start finding multiple structures that are all larger than the theoretical maximum, it starts to look like maybe the theory is the problem, not the observations. There's another structure called the Claus-Campusano Large Quasar Group, or LQG, which was actually discovered back in 1991, long before the Huge-LQG. It's about 2 billion light-years across, which is still larger than the theoretical maximum, but it didn't get as much attention at the time because the theoretical framework around the cosmological principle wasn't as well developed. But it's still there, and it's still a problem for the Standard Model. Then there's the matter of protoclusters, these massive collections of galaxies in the early universe that are in the process of merging together to form galaxy clusters. We talked about the Phoenix cluster earlier, which is a mature galaxy cluster with thousands of galaxies. But protoclusters are the precursors to structures like Phoenix. They're regions of space where galaxies are packed more densely than average, and they're all in the process of falling toward each other, pulled together by gravity over the course of hundreds of millions of years. One of the most extreme protoclusters discovered is called SPT 2349-56. This thing is absolutely wild. It's located about 12.4 billion light-years away, which means we're seeing it as it was when the universe was only about 1.4 billion years old, roughly 10% of its current age. SPT 2349-56 contains 14 galaxies that are all in the process of merging together in a region of space that's only about 3 times the size of the Milky Way. 3 times the size of the Milky Way. That is incredibly tiny for 14 entire galaxies. These galaxies are packed so densely together that they're essentially on top of each other, and they're all moving at hundreds of kilometers per second, smashing into each other, merging, exchanging gas and stars. The total mass of SPT 2349-56 is estimated to be around 10 trillion solar masses, and that's just the 14 core galaxies. Surrounding the core, there are roughly 50 additional galaxies that are also part of the larger structure. Over time, all of these galaxies are going to merge together into a single massive galaxy cluster, probably something similar to the Phoenix cluster or even larger. But here's the thing that makes SPT 2349-56 so interesting from a cosmological perspective. It exists at a time when the universe was only 1.4 billion years old. That's incredibly early in the history of the universe, and the question is, how did such a massive structure have time to form so early? According to the Lambda CDM model, structures form hierarchically. Small structures form first, things like individual galaxies and small galaxy groups, and then over time those small structures merge together to form larger structures like galaxy clusters and superclusters. It's a bottom-up process, and it takes time, a lot of time. The universe needs billions of years for gravity to pull matter together and build up the largest structures we see today. But SPT 2349-56 seems to have formed way too quickly. The universe was only 1.4 billion years old when this protocluster existed, and yet it's already massive, already in the process of forming what will eventually be one of the largest galaxy clusters in the universe. How did it get there so fast? This is another one of those questions that challenges the standard model. If structures can form this quickly, this early in the universe's history, then maybe our models of structure formation are missing something. Maybe the early universe was lumpier than we thought, with larger fluctuations in density that allowed massive structures to form more quickly than the models predict. Or maybe there's something about the process of galaxy and cluster formation that we don't fully understand. Either way, SPT 2349-56 is a puzzle, and it's one that cosmologists are still trying to solve. Now, I want to step back for a second and talk about what all of this means for the cosmological principle and for our understanding of the universe as a whole. Because the discovery of these massive structures, the Huge-LQG, the Klaus-Campasano-LQG, protoclusters like SPT 2349-56, these are not just isolated curiosities. They're part of a larger pattern that suggests the universe might not be as homogeneous on large scales as we thought it was. And if the universe is not homogeneous on large scales, then the cosmological principle is wrong, or at least incomplete. And if the cosmological principle is wrong, then we need to rethink a lot of our assumptions about cosmology. Now, I'm not saying that the cosmological principle is definitely wrong. I want to be clear about that. The evidence is not conclusive, and there are still a lot of uncertainties in the observations, but what I am saying is that there are cracks forming in the foundation of the standard model, and these massive structures are some of the biggest cracks. They're raising questions that we don't currently have good answers to, and they're pushing the boundaries of what our theories can explain. One of the key issues is that the universe is only 13.8 billion years old. That's not a lot of time on cosmic scales. In order for structures like the Huge-LQG to form, you need matter to clump together under gravity over billions of years. But if a structure is 4 billion light-years across, that means that matter on one side of the structure would need to have been gravitationally communicating with matter on the other side of the structure, pulling it together for billions of years. The problem is that the speed of light limits how fast information, including gravitational information, can travel through the universe. If the universe is only 13.8 billion years old, and a structure is 4 billion light-years across, then how did the matter on opposite sides of the structure have time to gravitationally interact and form a coherent structure? The numbers just don't quite add up. And then there's the issue of dark energy. We know that dark energy is causing the expansion of the universe to accelerate. On scales larger than about 10 million light-years, dark energy dominates over gravity, and space is expanding faster and faster. That means that on the scales we're talking about here, billions of light-years, the expansion of space is incredibly strong. It's pulling things apart, making it even harder for gravity to clump matter together into large structures. And yet, despite the expansion, despite the limited time since the Big Bang, these massive structures exist. It's a genuine puzzle. Some cosmologists have proposed that maybe the cosmological principle only applies on even larger scales than we thought. Maybe the universe isn't homogeneous until you zoom out to scales of 10 billion light-years or more. But that's a difficult pill to swallow because it means that a huge fraction of the observable universe, which is 93 billion light-years across, is not homogeneous. It means that we're living in a universe that's much lumpier, much more structured than the standard model predicts. And it raises the question, if the universe is this lumpy on such large scales, does that mean we are in a special location after all? Are we living in an unusually dense or unusually empty region of the universe? And if so, what does that mean for the Copernican principle and the idea that we don't occupy a special place in the cosmos? These are deep philosophical questions, and they're also deeply scientific questions. They're the kinds of questions that get to the heart of what cosmology is all about. Understanding the structure and evolution of the universe on the largest scales possible. And right now, we don't have definitive answers. We have observations that are difficult to explain within the framework of the standard model, and we have theories that make predictions that don't always match up with what we see. That's the nature of science. It's messy, it's uncertain, and it's constantly evolving as we gather more data and refine our models. But the discovery of these massive structures, these forbidden walls that seem to violate the cosmological principle, is a reminder that the universe is full of surprises. Just when we think we've got it all figured out, nature throws us a curveball, and that's what makes cosmology so exciting. We're not just passively observing the universe, we're actively challenging our understanding of it, pushing the boundaries of our theories, and discovering things that genuinely make us question some of our most fundamental assumptions. And speaking of massive structures that challenge our understanding, the Huge-LQG is not even the largest structure we've discovered. There's something even bigger out there, something so absurdly massive that it dwarfs even the Huge-LQG. It's a structure that spans a significant fraction of the observable universe, a cosmic wall of galaxies stretching across 10 billion light-years of space. And we're going to dive into that structure next, because if the Huge-LQG is a problem for the cosmological principle, this next structure is an absolute nightmare. It's called the Hercules Corona Borealis Great Wall, and it's the largest known structure in the entire universe. So, in the last chapter, we talked about massive structures that seem to violate the cosmological principle, structures like the huge large quasar group that span billions of light-years and genuinely challenge our understanding of how the universe should be organized. We talked about how the standard model of cosmology predicts that there should be a maximum size for structures in the universe, somewhere around 1.2 to 1.5 billion light-years, and how anything significantly larger than that is a problem for the theory. We talked about protoclusters forming way too early in the universe's history and large quasar groups that are way too large to fit comfortably within our models. These are all cracks in the foundation of the standard cosmological model, and they're raising some really uncomfortable questions about whether the universe is truly as homogeneous as we've been assuming. But here's the thing, and I need you to understand this. Everything we talked about in the last chapter, all of those massive structures that seem to defy the cosmological principle, they're all small potatoes compared to what we're about to discuss now. Because there is a structure out there in the cosmos, a structure so absurdly, incomprehensibly massive that it makes the huge large quasar group look tiny by comparison. This structure is so large that according to every model we have, according to the lambda CDM model, according to the cosmological principle, it simply should not exist. And yet it does. It's there, we've mapped it, we've studied it, and we have no idea how to explain it. This structure is called the Hercules Borealis Great Wall, and it is the largest known structure in the entire observable universe. And when I say largest, I'm not being hyperbolic. This thing spans 10 billion light-years across. 10 billion light-years. To put that into perspective, that's roughly 10% of the diameter of the entire observable universe. It's so large that you could fit 94,000 Milky Way galaxies side by side along its length and still not reach from one end to the other. This structure is genuinely one of the most bizarre and controversial discoveries in modern cosmology, and it's forcing us to seriously reconsider some of our most fundamental assumptions about how the universe works. Now, before we dive into the specifics of the Hercules Borealis Great Wall, which I'm just going to call the Great Wall for the rest of this chapter, because saying Hercules Borealis Great Wall every time is a mouthful, we need to talk about how astronomers even go about mapping these massive structures in the first place. Because it's not like you can just point a telescope at the sky and see a giant wall of galaxies stretching across billions of light-years. Most of these structures are so far away that the individual galaxies within them are incredibly faint, and it takes years of observations and sophisticated data analysis to piece together the larger picture. The way astronomers map large-scale structures has evolved significantly over the past few decades, and it's one of the most impressive achievements in observational astronomy. The key tool that astronomers use to map large-scale structures is something called a galaxy survey. A galaxy survey is exactly what it sounds like. Astronomers systematically observe large regions of the sky, catalog every galaxy they can see, measure the distance to each galaxy, and then use all of that data to create a three-dimensional map of how galaxies are distributed in space. These surveys have been going on for decades now, and they've allowed us to create incredibly detailed maps of the cosmic web, those filaments and voids that span the universe. One of the first major galaxy surveys was called the CFA Redshift Survey, which was conducted in the 1970s and 80s. This survey mapped out the positions and distances of thousands of galaxies in a relatively small region of the sky, and it was the first survey to reveal the large-scale structure of the universe in any real detail. What astronomers found was shocking at the time. Galaxies were not distributed randomly. They were organized into these long filamentary structures with huge voids in between. It was the first direct evidence of the cosmic web, and it completely changed how we think about the universe. Then came the Sloan Digital Sky Survey, or SDSS, which started in the year 2000 and is still ongoing today. The SDSS has mapped out the positions and distances of hundreds of millions of galaxies across a huge fraction of the sky, creating the most detailed three-dimensional map of the universe ever made. The data from the SDSS has been used in thousands of scientific papers, and it's been absolutely crucial for understanding how galaxies and large-scale structures have evolved over cosmic time. It's honestly one of the most successful scientific projects of the 21st century. Now, when astronomers create these maps, they're not just plotting the positions of galaxies, they're also measuring something called redshift, which is a key concept in cosmology. Redshift is a measure of how much the light from a distant galaxy has been stretched as it travels through the expanding universe. The more the light is stretched, the more it shifts toward the red end of the spectrum, hence the term redshift, and the amount of redshift tells you how far away the galaxy is. The higher the redshift, the more distant the galaxy, and the further back in time you're seeing it. So by measuring the redshift of galaxies, astronomers can figure out not just where they are in the sky, but also how far away they are in three-dimensional space. When you plot out all of these galaxies in 3 dimensions, the cosmic web becomes incredibly clear. You see these long filaments of galaxies stretching across hundreds of millions of light years, connecting galaxy clusters and superclusters. And between the filaments, you see voids, these vast, empty regions of space with very few galaxies. The cosmic web is the largest scale structure in the universe, and it's the result of how matter has clumped together under gravity over the past 13.8 billion years since the Big Bang. One of the most famous structures discovered through these galaxy surveys is something called the Sloan Great Wall. The Sloan Great Wall was discovered in 2003 using data from the Sloan Digital Sky Survey, and it's a massive filament of galaxies that spans about 1.37 billion light-years. At the time of its discovery, it was the largest known structure in the universe, and it was already pushing the boundaries of what the cosmological principle would allow. But the Sloan Great Wall is tiny compared to the Great Wall we're talking about today. Now there's another technique that astronomers use to map large-scale structures, and this is the technique that was used to discover the Hercules corona Borealis Great Wall. Instead of mapping galaxies directly, astronomers can look at the distribution of gamma-ray bursts, or GRBs. Gamma-ray bursts are some of the most energetic events in the entire universe. They're short-lived flashes of gamma rays, the most energetic form of light, and they're caused by extremely violent events like the collapse of massive stars into black holes or the merger of two neutron stars. A single gamma-ray burst can release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. They're absolutely cataclysmic events, and they're so bright that we can see them from the other side of the universe. Now, here's the key thing about gamma-ray bursts. They only happen in regions of space where there's a lot of massive stars. Massive stars are short-lived, typically only lasting a few million years before they explode in supernovae or collapse into black holes. And massive stars tend to form in regions of space where there's a high density of gas and matter, which are the same regions where you find large concentrations of galaxies. So if you map out where gamma-ray bursts are occurring in the universe, you're essentially mapping out the distribution of mass. Regions with a lot of gamma-ray bursts are regions with a lot of matter. Regions with very few gamma-ray bursts are regions with less matter, like voids. This technique of using gamma-ray bursts as traces of large-scale structure is really clever, and it's allowed astronomers to map out the distribution of matter in the distant universe in a way that wouldn't be possible with galaxy surveys alone. Because gamma-ray bursts are so bright, we can detect them from incredibly far away, much farther than we can see individual galaxies. This means we can use gamma-ray bursts to probe the structure of the universe at much earlier times, seeing how matter was distributed billions of years ago when the universe was much younger. And that brings us to November of 2013, when a team of astronomers led by Istvan Horvath, John Hakila, and Zsolt Bagoli announced a discovery that sent shockwaves through the astronomical community. They had been analyzing the distribution of gamma-ray bursts detected by various satellites over the past few decades, and they noticed something really strange. There was a region of the sky where gamma-ray bursts seemed to be clustered together far more than you'd expect by random chance. And when they calculated the distances to these gamma-ray bursts based on their redshifts, they realized that they were all located at roughly the same distance from Earth, about 10 billion light-years away. And they were all located in the same general region of space, in the direction of the constellations Hercules and Corona Borealis. When the team mapped out the full extent of this clustering, they realized they were looking at something absolutely massive. This was not just a galaxy cluster or even a supercluster. This was a structure that spanned roughly 10 billion light-years from one end to the other. 10 billion light-years. That is so large that it's genuinely difficult to comprehend. To put it into perspective, the Sloan Great Wall, which was the largest known structure at the time and already considered shockingly large, is about 1.37 billion light-years across. The Great Wall is over 7 times larger than that. It's also significantly larger than Laniakea, the supercluster we're a part of, which spans about 520 million light-years. The Great Wall is nearly 20 times larger than Laniakea. It dwarfs everything else we've ever discovered. The thickness of the Great Wall is also absolutely absurd. Depending on how you measure it, the structure is somewhere between 7.2 and 9.2 billion light-years thick. Some measurements even suggest that it extends over 1 billion light-years in the radial direction, meaning it's not just a thin wall, but a genuinely three-dimensional structure with enormous volume. This is not a simple filament like the ones we see in the cosmic web. This is a massive concentration of matter spanning a significant fraction of the observable universe. Now, when this discovery was announced, the reaction from the astronomical community was a mixture of fascination and skepticism. On the one hand, the data was there, the gamma-ray bursts were real, the clustering was statistically significant, and the structure seemed to be genuine. But on the other hand, the implications of this discovery were absolutely staggering. Because according to the cosmological principle and the lambda CDM model, a structure this large should not exist. It's impossible. The maximum size for structures in the universe, as predicted by theory, is around 1.2 to 1.5 billion light-years. The Great Wall is roughly 7 to 8 times larger than that. It's not just slightly over the limit, it's way, way over the limit. And that's a huge problem. One of the key issues is the age of the universe. The universe is 13.8 billion years old. That means that light, which is the fastest thing in the universe and also the fastest that information can travel, has had 13.8 billion years to cross the cosmos. In order for a structure like the Great Wall to form, matter on one side of the structure needs to have been gravitationally interacting with matter on the other side of the structure, pulling it all together over billions of years. But if the structure is 10 billion light-years across, then light from one side of the structure would take 10 billion years just to reach the other side. That means that over the entire history of the universe, light has only had enough time to cross the Great Wall about 1.4 times. So how could gravity, which also propagates at the speed of light, have had enough time to pull all of this matter together into a coherent structure? It gets even worse when you consider when the Great Wall formed. The Great Wall is located about 10 billion light-years away from us, which means we're seeing it as it was 10 billion years ago. The universe was only about 3.8 billion years old at that time. So this massive structure, this 10 billion light-year wide concentration of matter, had already formed within the first 3.8 billion years of the universe's existence. That's less than 30% of the current age of the universe. How did it have time to form so quickly? According to the Standard Model, structures form hierarchically. Small things form first, and then they gradually merge together to form larger things over billions of years. It's a slow bottom-up process, but the Great Wall seems to have formed way too quickly. It's like finding a fully grown oak tree in a forest that's only been around for a few years. It just doesn't make sense. And then there's the issue of dark energy. We've talked about dark energy a few times in this video, but it's worth reiterating here because it's so important. Dark energy is this mysterious force that's causing the expansion of the universe to accelerate. On large scales, scales of tens of millions of light-years or more, dark energy dominates over gravity. It's pulling space apart, making it harder for gravity to clump matter together. And on the scale of the Great Wall, billions of light-years, dark energy is incredibly strong. It's fighting against gravity at every step, trying to pull the structure apart. So not only did the Great Wall have to form in a very short amount of time, it also had to form while fighting against the expansion of the universe driven by dark energy. It's honestly difficult to see how this could have happened within the framework of the Standard Model. When Isvan Horvath and his team published their findings in 2013, they were very careful to acknowledge the controversial nature of their discovery. Horvath said at the time, "This structure is so large that it's not easy to understand how it got there at all." And that's putting it mildly. The Great Wall is what's known in the scientific community as an anomaly. It's something that doesn't fit within our current understanding, something that challenges the models we've been using to describe the universe. And anomalies like this are both exciting and frustrating. They're exciting because they point to gaps in our knowledge, areas where we have more to learn. But they're frustrating because they don't come with easy answers. We can't just tweak a parameter in the models and make the Great Wall fit. The discrepancy is too large for that. If the Great Wall is real, and if it's as large as it appears to be, then we might need to fundamentally rethink some of our assumptions about cosmology. Now, I mentioned earlier that there was skepticism about the discovery, and I want to be clear about what that skepticism is based on. Because it's not that astronomers think Horvath and his team faked the data or made a mistake. The gamma-ray bursts are real, and the clustering is statistically significant. The skepticism is more about whether the clustering represents a real, coherent structure or whether it's just a statistical fluctuation. Remember, when you're dealing with large-scale structures in the universe, the definition of a structure becomes somewhat ambiguous. Unlike a galaxy cluster, which is clearly a gravitationally bound system with a well-defined boundary, something like the Great Wall is much more fuzzy. It's a region of space where the density of matter is higher than average, but it's not a single unified system. The gamma-ray bursts that define the Great Wall are spread out over an enormous volume of space, and they're definitely not gravitationally bound to each other. So the question is, are we looking at a real, coherent structure, or are we just seeing a random fluctuation in the density of gamma-ray bursts that happens to look like a structure when viewed from Earth? If you take a large enough volume of the universe and look for patterns, you're going to find patterns just by chance. It's the same issue we talked about with the huge large quasar group in the last chapter. The human brain is very good at finding patterns, even when those patterns are just noise. And when you're dealing with cosmological data, where you're analyzing the positions of thousands of objects spread out over billions of light years, it's really easy to find patterns that look significant but are actually just random. Some astronomers have argued that the Great Wall might not be a real structure, that it's just a chance alignment of gamma-ray bursts that happen to be located in the same general region of space when viewed from our vantage point on Earth. If that's the case, then the Great Wall is not a violation of the cosmological principle. It's just an illusion, a trick of perspective. But Horvath and his team have run the statistics, and they've determined that the probability of seeing a clustering this strong by random chance is extremely small. They've calculated what's called a p-value, which is a measure of statistical significance, and they've found that the clustering is significant at a level that would be considered very unlikely to occur by chance. In their 2014 follow-up paper, they refined their measurements and confirmed that the structure is real and that its extent is even larger than they initially thought. In fact, in more recent studies, parts of the Great Wall have been found to be closer to Earth than originally calculated, which has allowed astronomers to study them in more detail. But the more we study the Great Wall, the more questions it raises. The European Space Agency has even planned a mission called Theus, which is designed specifically to study gamma-ray bursts and the large-scale structures they trace. The hope is that Theus will be able to provide more detailed data about the Great Wall and help us figure out whether it's a real coherent structure or just a statistical anomaly. But here's the thing that makes the Great Wall so frustrating and so fascinating at the same time. Even if it is a real structure, we don't fully understand what we're looking at. Part of the problem is that the Great Wall is located in a region of the sky that's partially obscured by our own galaxy. There's a region called the Zone of Avoidance, which is the part of the sky that's blocked by the dust and gas in the Milky Way. When you try to look through the zone of avoidance, the light from distant galaxies and gamma-ray bursts is absorbed and scattered by all the junk in our own galaxy, making it really difficult to see what's actually out there. The Great Wall extends into the zone of avoidance, which means that we can't see the full extent of the structure. There could be even more to it that we're simply unable to observe because our view is blocked. So the true size of the Great Wall might be even larger than 10 billion light-years, which is a genuinely terrifying thought. The Great Wall has been described by some astronomers as an inconvenience for astronomers, which is a bit of an understatement if you ask me. It's more like a full-blown crisis for cosmology. Because if the Great Wall is real, and if it's as large as it appears to be, then the cosmological principle is in serious trouble. The cosmological principle is one of the foundational assumptions of modern cosmology. It's the idea that the universe is homogeneous and isotropic on large scales, that it looks the same no matter where you are and in which direction you look. And if that's true, then there should be a maximum size for structures in the universe. Anything larger than that maximum size would violate the principle of homogeneity. The Great Wall is so far beyond that maximum size that it's not even close. It's a massive outlier, a structure that simply should not exist in a homogeneous universe. So what are the possible explanations for the Great Wall? There are a few different ideas that have been proposed, but none of them are particularly satisfying. One possibility is that our models of structure formation are simply wrong. Maybe the universe doesn't form structures hierarchically in the way we think it does. Maybe there's some process we don't understand that allows matter to clump together on much larger scales and much faster timescales than the standard model predicts. If that's the case, then we need to go back to the drawing board and develop new models that can account for structures like the Great Wall. Another possibility is that the cosmological principle doesn't apply on the scales we thought it did. Maybe the universe doesn't become homogeneous until you zoom out to scales of tens of billions of light-years or more, much larger than the few 100 million light-years that we've been assuming. If that's the case, then the Great Wall is not a violation of the cosmological principle. It's just evidence that the scale at which the universe becomes homogeneous is much larger than we thought. But that would still be a pretty significant revision to our understanding of cosmology, and it would raise a lot of uncomfortable questions about whether we're living in a special location in the universe. A third possibility, and this is one that some cosmologists have seriously considered, is that the universe is not homogeneous at all, even on the largest scales. Maybe the cosmological principle is just wrong, and the universe is lumpy all the way up. If that's the case, then we need to completely rethink how we do cosmology. The lambda CDM model is built on the assumption that the universe is homogeneous on large scales, and if that assumption is false, then the entire model needs to be revised. This would be a huge deal, one of the biggest paradigm shifts in cosmology since the discovery of the expansion of the universe nearly a century ago. The truth is, we don't currently have a scientific consensus on how to explain the Great Wall. Different astronomers have different opinions, and the debate is ongoing. Some think it's a real structure that challenges the cosmological principle. Others think it's a statistical fluke that will go away with more data. And still others think that it's real but that we can explain it within the framework of the standard model if we're willing to push the model to its limits. The only thing everyone agrees on is that the Great Wall is a puzzle, and it's one of the most important puzzles in cosmology right now. What makes the Great Wall even more intriguing is that it's not just a problem for theory, it's also a window into the early universe. Remember, we're seeing the Great Wall as it was 10 billion years ago, when the universe was less than 4 billion years old. Studying the Great Wall gives us a unique opportunity to understand how matter was distributed in the early universe and how structures formed during that critical period of cosmic history. If we can figure out how the Great Wall formed, it might give us insights into the processes that shaped the entire universe. So here we are, staring at a structure that's 10 billion light-years across, a structure that spans 10% of the observable universe, a structure that formed within the first few billion years after the Big Bang, and a structure that, according to all of our models, should not exist. And yet it does. The Hercules Borealis Great Wall is out there, stretching across the cosmos, defying our understanding, challenging our theories, and forcing us to confront the possibility that we don't understand the universe as well as we thought we did. It's a humbling reminder that no matter how much we learn, no matter how sophisticated our models become, the universe is always going to be capable of surprising us. And as we continue to map the universe, as we build better telescopes and conduct more surveys and gather more data, who knows what else we're going to find? The Great Wall might not be the largest structure out there. There could be even larger structures lurking in the depths of space, structures that we haven't discovered yet because they're too far away or too faint or hidden behind the zone of avoidance. The universe is vast, and we've only scratched the surface of what's out there. But the Great Wall, as massive and controversial as it is not the end of the story. Because as large as it is, it's still just a structure within the observable universe. And the observable universe itself has an edge, a boundary beyond which we cannot see, no matter how powerful our telescopes become. That boundary is determined by the age of the universe and the speed of light, and it defines the limits of what we can ever hope to observe. But just because we can't see beyond that boundary doesn't mean there's nothing there. In fact, the universe almost certainly extends far beyond the edge of the observable universe, possibly infinitely far. And that raises a whole new set of questions about what's out there in the unobservable universe, what the universe looks like on scales even larger than what we can see, and whether there are structures out there that make even the Great Wall look tiny by comparison. And that's exactly what we're going to explore in the final chapter, the edge of the observable and what lies beyond. So we've spent this entire video climbing a ladder of cosmic scale, starting from our tiny little planet Earth and working our way up through the solar system, the Milky Way, galaxy groups, galaxy clusters, superclusters, and finally to massive structures like the Hercules Borealis Great Wall that span 10 billion light-years across. We've talked about structures so large they challenge our fundamental understanding of how the universe should be organized, structures that seem to violate the cosmological principle and push the boundaries of what our models can explain. But now, we need to address the elephant in the room. Because as massive as the Great Wall is, as incomprehensibly large as all of these structures are, they're all still contained within something even larger. They're all part of the observable universe. And the observable universe itself has an edge, a boundary beyond which we simply cannot see, no matter how powerful our telescopes become. That boundary is not a physical wall or a surface or anything like that. It's an information limit, a horizon beyond which light has not had enough time to reach us. And understanding that boundary, understanding the edge of the observable universe, is crucial to understanding our place in the cosmos and the limits of what we can ever hope to know. Now, when I say the observable universe, I need to be very specific about what I mean because there's a lot of confusion around this concept, and I've seen people get it wrong constantly. The observable universe is not the entire universe. Let me say that again because it's really important. The observable universe is not the entire universe. The observable universe is just the part of the universe that we can see from Earth, given the age of the universe and the speed of light. Light travels at about 186,000 miles per second, and nothing can move faster than light. That's one of the fundamental laws of physics as we understand them. So if the universe is 13.8 billion years old, which it is, then light from distant objects has had 13.8 billion years to travel through space and reach us. Anything farther away than that, anything so distant that light from it hasn't had time to reach us yet, is beyond the edge of the observable universe. We can't see it. We can't detect it. We have no way of observing it, at least not with current technology or any technology we can even conceive of. But here's where things get a bit weird, and this is where a lot of people get confused. You might think, okay, if the universe is 13.8 billion years old and light has had 13.8 billion years to travel, then the edge of the observable universe should be 13.8 billion light years away, right? Wrong. The edge of the observable universe is actually much farther away than that. It's about 46.5 billion light years away in every direction. That means the diameter of the observable universe is about 93 billion light years. 93 billion light years. Let me say that again because I know what you're thinking. How can the edge of the observable universe be 46.5 billion light years away if light has only been traveling for 13.8 billion years? That doesn't make sense. Light can't travel farther than the age of the universe multiplied by the speed of light. That would violate the laws of physics. But it's not violating the laws of physics. The reason the observable universe is so much larger than you'd expect is because of something we've touched on several times in this video, the expansion of the universe. You see, the universe is not static, it's expanding. It's been expanding ever since the Big Bang, and it's expanding faster and faster over time due to dark energy. When light leaves a distant galaxy and starts traveling toward us, that galaxy is a certain distance away. But while the light is traveling, the space between us and that galaxy is expanding. By the time the light reaches us, the galaxy is much farther away than it was when the light left it. This is called metric expansion, and it's one of the most important concepts in cosmology. Space itself is stretching, and that stretching affects the distance between objects. So even though the light from the most distant objects we can see has only been traveling for about 13.8 billion years, those objects are now about 46.5 billion light-years away because space has been expanding the entire time the light was in transit. This is honestly one of the most mind-bending concepts in all of cosmology, and it's something that even scientists struggled with for a long time. The expansion of the universe is not like an explosion where matter is flying outward through space. It's space itself that's expanding. Galaxies aren't moving through space away from us. Space is expanding between us and those galaxies. It's a subtle but incredibly important distinction, and this expansion is what gives us an observable universe that's much larger than you'd naively expect, just from multiplying the age of the universe by the speed of light. So, the observable universe has a radius of about 46.5 billion light-years, which gives it a diameter of about 93 billion light-years. And within that observable universe, we estimate there are about 2 trillion galaxies, 2 trillion, each one potentially containing hundreds of billions of stars, each star potentially hosting planets, each planet potentially harboring life. The numbers are so absurdly large that they genuinely lose all meaning. But 2 trillion galaxies is our current best estimate for how many galaxies exist within the observable universe, based on deep field observations from telescopes like Hubble and the James Webb Space Telescope. But here's something really important to understand. Not all of those galaxies are going to stay within the observable universe. Because the universe is not just expanding, it's expanding faster and faster over time. This acceleration is driven by dark energy, and it means that distant galaxies are moving away from us at speeds that are constantly increasing. In fact, the most distant galaxies we can currently see are receding from us faster than the speed of light. Now, before you start typing an angry comment about how nothing can move faster than light, let me clarify. These galaxies are not moving through space faster than light. That would violate relativity. But the space between us and those galaxies is expanding fast enough that the effective rate at which they're moving away from us exceeds the speed of light. And there's no law of physics that prevents space itself from expanding faster than light. It's space that's stretching, not the galaxies themselves moving through space. What this means is that over billions of years, more and more galaxies are going to cross what's called the cosmic event horizon and disappear from view. Their light will become so redshifted, so stretched out by the expansion of space, that it will eventually fade into the background radiation and become undetectable. Eventually, in the far future, trillions of years from now, observers in our galaxy will look out into space and see almost nothing. They'll see the stars in our own galaxy, and they'll see Andromeda, assuming we've merged with it by then. But beyond that, the universe will appear dark and empty. All the distant galaxies, all the rich structure we see today, will have disappeared beyond the cosmic horizon. It's a genuinely depressing thought, to be honest. Future civilizations, if they exist, will have no way of knowing that the universe was once filled with trillions of galaxies. They'll look out at the night sky and think they're alone in an empty cosmos. Unless, of course, they have access to records from our time, or unless they figure out some clever way to detect the remnants of those distant galaxies. But it's a reminder that we're living in a very special time in the history of the universe, a time when we can still see the large-scale structure and study the cosmos in all its richness and diversity. Now, let's talk about the edge of the observable universe and what we actually see when we look out to the farthest distances. The edge of the observable universe is not just empty space. There's something there, a very specific thing that we can observe, and it's one of the most important discoveries in all of cosmology. I'm talking about the cosmic microwave background, or CMB. The cosmic microwave background is a faint glow of radiation that fills the entire universe. It's left over from the Big Bang, and it's the oldest light in the universe. When you tune a radio or an old television to a channel with no signal and you see that static, about 1% of that static is actually the cosmic microwave background. You're literally seeing the afterglow of the Big Bang with your own eyes, or at least with your radio or TV. It's honestly one of the coolest things in physics. The cosmic microwave background was released about 380,000 years after the Big Bang. Now, 380,000 years might sound like a long time, but in cosmic terms, it's incredibly early. The universe is 13.8 billion years old now, so 380,000 years after the Big Bang is basically right at the beginning. Before this time, the universe was incredibly hot and dense. It was so hot that atoms couldn't even form. The entire universe was a hot, dense plasma of protons, electrons, and photons, all interacting with each other. The photons, which are particles of light, were constantly scattering off the free electrons in the plasma. This scattering made the universe opaque to light. You couldn't see anything because the light couldn't travel very far before it hit an electron and got scattered in a different direction. It was like trying to see through a thick fog. but as the universe expanded, it cooled down, and at about 380,000 years after the Big Bang, the universe cooled down enough for protons and electrons to combine and form neutral hydrogen atoms. This process is called recombination, even though it's technically the first time atoms were combining, not recombining, but the name stuck. Once neutral atoms formed, the photons were no longer scattering off free electrons. They were free to travel through space unimpeded. The universe became transparent to light for the first time. And the light that was released at that moment, the light from the hot plasma just before it cooled into neutral atoms, is what we see today as the cosmic microwave background. Now, when that light was released, it was incredibly hot. The temperature of the universe at the time of recombination was about 3,000 degrees Kelvin, which is hot enough to glow orange or red. But the universe has been expanding for the past 13.8 billion years, and as it expanded, the light from the cosmic microwave background got stretched out. The wavelengths of the light got longer and longer, shifting from visible light to infrared to microwaves. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin, which is just a few degrees above absolute zero. It's incredibly cold, and it's only detectable in the microwave part of the electromagnetic spectrum, which is why we call it the cosmic microwave background. The cosmic microwave background is remarkably uniform. If you measure the temperature in one direction and then measure it in another direction, you'll find that they're almost exactly the same. The variations in temperature are only about 1 part in 100,000. That's an incredibly high level of uniformity, and it tells us that the early universe was very smooth and homogeneous. But those tiny variations, those 1 part in 100,000 fluctuations, are incredibly important. They're the seeds of all the structure we see in the universe today. Those tiny overdense regions, where the temperature was slightly higher than average, eventually collapsed under gravity to form the first galaxies and the first galaxy clusters. And those tiny underdense regions, where the temperature was slightly lower, eventually became the voids we see in the cosmic web. Everything, all the structure in the universe, can be traced back to those tiny fluctuations in the cosmic microwave background. The cosmic microwave background was first discovered by accident in 1965 by 2 astronomers named Arno Penzias and Robert Wilson. They were working at Bell Labs, trying to build a sensitive radio antenna for communication purposes, and they kept picking up this annoying background noise that they couldn't get rid of. They thought maybe it was interference from nearby cities, or maybe it was pigeon droppings on the antenna. They even cleaned the pigeon droppings off the antenna, but the noise was still there. Eventually, they realized that the noise was coming from space, and that it was coming from every direction equally. They had stumbled upon the cosmic microwave background, the afterglow of the Big Bang. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery, and it's considered one of the most important discoveries in all of cosmology. Since then, the cosmic microwave background has been mapped in exquisite detail by several space missions. The first major mission was COBE, the Cosmic Background Explorer, which launched in 1989. COBE confirmed that the cosmic microwave background had the spectrum of a perfect blackbody, which is exactly what you'd expect from the hot plasma of the early universe. It also detected the tiny temperature fluctuations for the first time, providing the first direct evidence of the seeds of structure formation. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which launched in 2001 and provided much more detailed maps of the cosmic microwave background. And most recently, we've had the Planck satellite, which was launched by the European Space Agency in 2009 and provided the most detailed maps of the cosmic microwave background to date. The Planck mission's data has been absolutely crucial for refining our understanding of cosmology and the parameters of the lambda CDM model. When you look at a map of the cosmic microwave background, what you're seeing is a snapshot of the universe when it was only 380,000 years old. You're seeing the universe as a baby, and that snapshot is located about 46 billion light-years away from us now, accounting for the expansion of space. The cosmic microwave background forms a sphere around us, a shell that marks the edge of the observable universe. It's sometimes called the surface of last scattering because it's the surface where photons last scattered off electrons before the universe became transparent. Beyond that surface, we can't see anything. The universe was opaque before that time, so there's no light from earlier times that can reach us. The cosmic microwave background is, in a very real sense, a wall. It's not a physical wall, but it's an information wall. It's the farthest back in time we can see using light. It's the edge of the observable universe. Now, I want to address a common misconception because I see this all the time and it drives me crazy. Some people think that the cosmic microwave background is the edge of the universe, that beyond it there's just nothing. But that's not true. The cosmic microwave background is just the edge of the observable universe. It's the limit of what we can see from Earth given the age of the universe and the speed of light. But the universe almost certainly extends far beyond the cosmic microwave background. There's no reason to think that the universe just stops at the edge of what we can see. That would be incredibly anthropocentric, like thinking that the Earth is the center of the universe just because that's where we happen to be. The universe doesn't care about our perspective. It doesn't care about what we can or can't observe. The universe just is, and it extends in all directions, probably far beyond what we can ever hope to see. So, how big is the entire universe, not just the observable part? The honest answer is, we don't know. We have absolutely no idea. The universe could be just slightly larger than the observable universe, or it could be vastly larger, or it could even be infinite in size. We simply don't have enough information to say for sure, but based on our current understanding of cosmology, and based on a theory called cosmic inflation which describes how the universe expanded incredibly rapidly in the first fraction of a second after the Big Bang, most cosmologists think that the entire universe is much, much larger than the observable universe. Some estimates suggest that the entire universe could be at least 10 to the power of 23 times larger than the observable part. That's a 1 followed by 23 zeros. That number is so large that it's genuinely meaningless. But the point is, the universe we can see is probably just a tiny, tiny fraction of the whole thing. Think about it this way. Imagine you're standing in the middle of a huge desert, and you can only see as far as the horizon in every direction. The horizon is the limit of what you can see, but you know that the desert extends far beyond the horizon. You can't see what's out there, but you have no reason to think that the desert just ends at the horizon. It probably keeps going. The same thing is true for the universe. The observable universe is just the part we can see from our vantage point on Earth. Beyond the cosmic horizon, beyond the cosmic microwave background, the universe almost certainly keeps going. There are probably more galaxies out there, more stars, more planets, more structure, more of everything. We just can't see it because the light from those regions hasn't had time to reach us yet. And here's something that really blows my mind. If the universe is truly infinite in size, which is a real possibility, then there are an infinite number of galaxies out there, an infinite number of stars, an infinite number of planets. And if there are an infinite number of planets, then the probability of finding another planet exactly like Earth, with the exact same history, the exact same people, everything identical down to the atomic level, approaches certainty. There could be an infinite number of copies of you out there in the unobservable universe, living out every possible variation of your life. It's a genuinely bizarre thought, and it's one of the strange implications of an infinite universe. Of course, we have no way of testing this. We can't observe those other copies of Earth even if they exist, because they're beyond the cosmic horizon. But it's a fun thought experiment, and it highlights just how weird and wonderful the universe can be when you really think about the implications of infinity. Now, there's another concept related to the edge of the observable universe that I want to touch on, and that's the idea of the cosmic horizon and causality limits. We've talked about how the observable universe is defined by the distance that light has had time to travel since the Big Bang. But there's another horizon that's even more important in some ways, and that's the cosmic event horizon. The cosmic event horizon is the boundary beyond which events happening right now will never be observable to us, no matter how long we wait. Because the universe is expanding, and because that expansion is accelerating due to dark energy, there are regions of space that are receding from us faster than light. Light from those regions will never reach us, no matter how long we wait. Those regions are beyond our cosmic event horizon. The cosmic event horizon is currently located at a distance of about 16 billion light-years from us. That means that if an alien civilization in a galaxy located 16 billion light-years away decided to send us a message right now, that message would never reach us. The space between us and them is expanding too fast. The light or radio waves carrying the message would be fighting against the expansion of space, and they would lose. They would never be able to cross the gap. We are causally disconnected from anything beyond our cosmic event horizon. We can never interact with it. We can never observe it. We can never communicate with it. It's effectively a different universe as far as we're concerned. And as the universe continues to expand and accelerate, that cosmic event horizon is going to shrink. More and more of the universe is going to become causally disconnected from us. Galaxies that are currently within our cosmic event horizon will eventually cross it and disappear beyond the boundary of what we can ever observe or interact with. It's a genuinely sobering thought. The universe is not just vast, it's also fundamentally lonely. There are vast regions of space that we will never be able to reach, never be able to communicate with, never even be able to see. They might as well not exist as far as we're concerned. But here's the thing that I find absolutely fascinating about all of this. Despite the fact that the observable universe has an edge, despite the fact that there are regions of space we can never see or interact with, we've still learnt an incredible amount about the universe. We've mapped the cosmic microwave background. We've traced the evolution of galaxies over billions of years. We've discovered dark matter and dark energy. We've found structures like the Hercules Borealis Great Wall that challenge our understanding of cosmology. We've done all of this from a tiny planet orbiting an average star in a fairly typical galaxy. We've never left our solar system as a species, and yet we've managed to figure out the age of the universe, the rate at which it's expanding, the density of matter and energy, the distribution of galaxies across billions of light-years. It's honestly one of the greatest achievements in human history. The fact that we can sit here on Earth and figure out what the universe looked like when it was only 380,000 years old, that we can map out structures that span 10 billion light-years, that we can understand the fundamental forces and particles that govern reality, it's genuinely awe-inspiring. And we're not done. We're still exploring, still building better telescopes, still gathering more data, still refining our models. The James Webb Space Telescope, which launched in late 2021, is already revolutionizing our understanding of the early universe. It's peering deeper into space and further back in time than any telescope before it, and it's finding galaxies that formed only a few 100 million years after the Big Bang. We're living in a golden age of cosmology, a time when our observational capabilities are advancing faster than ever before. And who knows what we're going to discover next? Maybe we'll find evidence that challenges the cosmological principle even more than the Great Wall does. Maybe we'll find a way to probe beyond the cosmic microwave background and learn something about the universe before recombination. Maybe we'll even find evidence of other universes, other bubbles of space-time existing alongside our own in some higher dimensional multiverse. The possibilities are endless, and that's what makes cosmology so exciting. But at the same time, we have to be humble. We have to acknowledge that there are limits to what we can know. The observable universe is only a tiny fraction of the whole, and there are vast regions of space that we will never be able to observe. There are questions we may never be able to answer. What came before the Big Bang? What caused the Big Bang? Is the universe finite or infinite? Is our universe the only one, or are there others? These are profound questions, and some of them may be fundamentally unanswerable. Not because we're not smart enough, or because we don't have good enough technology, but because the information we would need to answer them is simply not accessible to us. It's beyond the cosmic horizon, beyond the reach of light, beyond the limits of what can ever be observed. And yet, despite those limits, despite the fact that we're confined to a tiny bubble of observable space within a possibly infinite cosmos, we keep searching, we keep asking questions, we keep pushing the boundaries of our knowledge, because that's what humans do. We're a curious species. We look up at the night sky and we wonder. We want to know where we came from, what our place is in the universe, whether we're alone. And even if we can't answer all of those questions, even if some of them remain forever out of reach, the journey of discovery is worthwhile in and of itself. Every new galaxy we discover, every new structure we map, every new insight we gain into the nature of reality, it all adds to our understanding of the cosmos and our place within it. So, we've reached the end of our journey through the largest objects in the universe. We started with Earth, a tiny planet in a vast cosmos. We expanded our view to include the solar system, then the Milky Way, then the local group, then galaxy clusters, then superclusters, then massive walls and filaments spanning billions of light years. And now, finally, we've reached the edge of the observable universe itself, the cosmic microwave background, the surface of last scattering, the farthest boundary of what we can ever hope to see. We've climbed the ladder of cosmic scale, from the smallest to the largest, and at every step we've been confronted with the sheer incomprehensible vastness of the universe. The numbers are so large they've lost all meaning. The scales are so enormous that our brains simply cannot process them. And yet, here we are, a species of curious apes on a tiny rock in the middle of nowhere, trying to make sense of it all. And I think that's beautiful. I think that's what makes us human. We're tiny, insignificant specks in an unimaginably vast cosmos, and yet we dare to ask the biggest questions. We dare to wonder what lies beyond the cosmic horizon, what came before the Big Bang, whether we're alone in the universe. And even if we never find all the answers, the fact that we're asking the questions is enough. Because in the end, the universe may be vast and impersonal and indifferent to our existence, but we're here and we're trying to understand it. And that matters. That's our legacy as a species. We're the universe trying to understand itself, and that's pretty damn cool. So here we are. We started this video standing on Earth, a planet 12,742 kilometers wide, thinking that was big. Then we zoomed out to the Sun, 1,000,000 times more massive, Then to the Milky Way, stretching 100,000 light-years across and containing hundreds of billions of stars. Then to Laniakea, our supercluster, spanning 520 million light-years. Then to the Phoenix cluster, one of the most massive gravitationally bound structures in existence. Then to the Hercules corona Borealis Great Wall, a structure 10 billion light-years across that genuinely shouldn't exist according to our models. And finally, to the edge of the observable universe itself, 93 billion light-years in diameter, containing 2 trillion galaxies, each one a universe unto itself. And after all of that, after climbing that incomprehensible ladder of scale, we're forced to confront a genuinely humbling truth. The observable universe is probably just a tiny fraction of the whole. Beyond the cosmic horizon, beyond the cosmic microwave background, the universe almost certainly keeps going. There could be structures out there that make the Great Wall look tiny. There could be an infinite cosmos stretching on forever, filled with galaxies and stars and planets we will never see, never interact with, never even know about. We're confined to our tiny bubble of observable space, a cosmic island surrounded by an ocean of the unknowable. But you know what? That's okay. Because despite being trapped on this tiny rock in the middle of an incomprehensibly vast cosmos, we've managed to figure out so much. We've mapped the structure of the universe across billions of light-years. We've discovered dark matter and dark energy. We've traced the evolution of galaxies back to when the universe was less than 1 billion years old. We've peered back in time to 380,000 years after the Big Bang and seen the afterglow of creation itself. From our tiny vantage point, we've managed to understand the cosmos in ways that would have been unimaginable just a century ago. And we're not done. We're still exploring, still discovering, still pushing the boundaries of what we can know. The universe may be vast and indifferent to our existence, but we're here and we're trying to understand it, and that matters, because in the end, we're just the universe trying to understand itself. And if that's not the most beautiful, profound thing in existence, I don't know what is.